test, test, test. Probably helpful to remember some poems or something like that for these occasions. Okay. Is the slide good? Perfect. Oh, that's probably on my end. There you go. That's like one of those eye thingies. And I suppose my computer's. Should probably just kill it just in case. Most people are, so not many typing roles. I mostly focus on high-level things. So I'll begin by asking the main question that I'm trying to solve, which is how should programming languages incorporate concurrency? But this is ICFP, so hopefully I can just slide this in without too much justification. And when I talk about how functional programming languages incorporate concurrency, there seems to be two common approaches, I guess. One is what I call the soup method, and it's not derogatory at all. But essentially the idea is that you take your language and you just add the appropriate primitives. You pick your model of concurrency, and then you add the appropriate primitives and make sure that this is all a safe thing to do. Okay, and I think the biggest criticism one can have for this is that it's not a very modular way to add features. So one can say it bloats the language. And because it's non-modular, it could interact with the non-concurrent features that already exists. So scalability is a bit harder in the future. And the other common approach is, well, you just have a library, right? You take your library, and then, well, you take your language and you just implement whatever concurrent abstractions you're trying to have in that library. And typically the way you do it is you have to implement the concurrency somehow. So you might want to use certain concurrency primitives that already exist in your language. Or you might have to go through like unsafe features. You might have to escape your language, make OS calls. So you know, there's some ad hocness. And a lot of implementations may sort of leave the safety of their current language. So that's not perfectly satisfying. And so I want to propose a different approach, a new approach maybe, which is to reframe this entire problem as interoperability. So instead of thinking about how do I add concurrency to my language, I want to say, let's have a separate language that's specialized for concurrency. And then now I can ask the following question. How do non-concurrent languages interact with concurrent languages? And in this paper, the non-concurrent language representative is just a simple, pure functional programming language. And the concurrent language is the session-typed message passing process calculus. OK, former I probably don't need to explain in too much detail. Latter I will explain a bit later. But before I sort of go into some of the technical details, just a little table of like why this is not such an obvious thing that you can do. So first of all, the functional language we're looking at is pure. And process calculi are inherently effectful. And their effects are they're sending and receiving messages. So it's not like you can monitor some memory and look at the memories being mutated. No, it's more like what messages are being passed. OK? And well, the other is functional language is functional in the sense that the formalization is very natural deduction-like. So if you look at it from a logical perspective, process calculi tend to be in a sequent calculus formulation. And so they're not entirely immediately compatible. And finally, the functional language I'm looking at is just an ordinary functional language, no substructure needed. So it has no restrictions on variable usage. But a session-typed process calculus has linearity, has a linear type system. So like, how do I make sure they don't interfere with one another? So that's another question. And if you look at the paper, you'll see like 4 bullet points of the contributions that I promised. So I'll read the summarized version of that. So 1, it's a type-safe foundation for concurrent programming. And the way I do it is that I separate ordinary programming with all the concurrency primitives. So it's more modular. OK, and if you're familiar with process calculus, we had to reinvent some standard semantics to fit our model. And if you're into metaprogramming, we also do type-safe code transformations. We can recurse through code, open code, and it's done in a type-safe way. And finally, if you, I don't know, I would say if you're a practical-minded person, but this is a prototype implementation, so it's not like a real super efficient implementation. But there is an implementation of our language and some examples of using some of the core features of our language. So that's also in the artifact. But in this talk, it's just number 1 that I'll focus on. And I'll mostly focus on the syntax, stay high level, and give some examples as I go through and give intuition. So first of all, as I promised, here are session types. You see this big sequent, and you get maybe a bit overwhelmed. But the gamma refers to a persistent functional context. Delta refers to your linear channel context. And C on the right is the session type. So the lowercase c is this. It comes from this intuitionistic formulation where you divide channels into a role. You have client channels at delta and 1 unique offering channel on the right. And the way you interpret these channels depends on which direction you're in. So here's a session type 1. It's the unit of tensor. And if you have a channel of type 1 to your left, so that's in delta, what the process has to do is it has to wait for the channel to close. And if you have a channel of type 1 on the right, then you have to close your channel. You have to terminate. So you can sort of see the send-receive paradigm going on, where one side is always going to be receiving, and the other side is going to be sending. So this is what ensures that this whole system is safe. OK, I want to introduce another type. Value output, I read this as tau and a. So look, we should look at this from the offering channel first. Essentially, we're just sending a value of type tau, and we're going to continue as type a for whatever a says. And so the client, as the client, you must receive a value of type tau and continue as type a. And then there's the dual to that, which is implication or value input, where in the offering channel you're receiving, but in the client, since the offering guy is receiving, you have to be sending. So that's roughly the game with session types. So here's and there are more, but we won't cover that. So here's some quick examples. Here's an example. I have a closed process, so it has no channels to the left. And I send 2 numbers through my offering channel, and then I terminate. So the type of that is nat and 1, because I send a nat, and then I send a nat, and then I terminate. OK. Next example, I'll receive 2 numbers from my left channel called lowercase a. So in the process, you'll see that I'm receiving 2 natural numbers, x and y. I'm waiting for it to terminate. And then I'm going to send the sum x plus y across my channel C. And therefore, the type of my channel C, the offering channel, is just nat and 1, because I'm only sending 1 number. Whereas my left channel A is nat and 1, because I'm receiving 2 numbers. OK? And now what makes this session type process calculus system concurrent is that we have process composition. So I'm just giving a meta-theoretic assignment of our 2 prior examples, the process that sends 2 numbers and the process that receives 2 numbers and sends its sum. And so you can compose them together. And you can see I've conveniently picked examples such that this P process sends 2 numbers, and this Q process depends on this channel A in a way that it receives 2 numbers. Essentially, the session types have to be the same, otherwise they can't communicate. OK? So that's all the background I'll give on session types. And now I'll talk about the functional programming side. And now you see rules, and maybe you get scared, but these are just rules that we've seen everywhere. This is just a simply typed lambda calculus. The only weird thing is you'll see these sigmas that I haven't talked about. So I'll talk about that later. And you also notice that the turnstiles are not turnstiles. This is just to distinguish it from the process calculus typing, which are turnstiles. Okay. And the idea is that I want to combine this session type system that I introduced to this simple functional language. And the main idea is first class code. So I want the functional language to be able to capture and generate open process code. And I want to be able to splice it and compose them, manipulate them. I want to be able to pattern match on it recursively. And I also want to be able to run these processes and also observe some behavior about them. So I won't talk about 3, but I'll talk about 1, 2, and 4. So I'll begin with 1 and 2. So here's a typing rule that I do have to explain in detail. This is the box introduction rule. But essentially what's going on is that this is a functional term, this box term. And what it does is it captures an open process P. And moreover, it captures its environments as well. So the process can be open. Think of this as like quoting open code. And the type of that is in this curly bracket. It's a contextual type. But essentially, all you have to know for this contextual type is that it contains all the information needed to sort of type this underlying process. And if you look at the premise, you'll see that it's a process typing judgment. See, it's the normal turnstile. So we defer entirely to the typing of the process calculus. And the functional programming language has nothing to do with type checking whatever's inside this box code. Okay? And the eliminator for this is just a let style eliminator. So M is going to be the process type. And N is the continuation. It gets to use this process as variable U. But now U is in sigma. So this is the first time we're using sigma. And one thing I want to mention before I finish my discussion about sigma is that if you look at the box introduction rule, you'll see that the functional context gamma prime does not appear, is not available in the process. This is essentially to ensure hygiene, as the racket people might call it. Essentially, that changing scopes will not affect anything. So it has its own functional context. But sigma seems to persist. And essentially, I use sigma to hold all metaprogramming related assumptions. OK, oops. So here's the example. We have our 2 example processes, the process that sends 2 numbers and the process that receives 2 numbers and sends their sum. Now, it's not a meta-theoric operation. I can quite literally capture these codes as variables, P and Q, using the box and the left box constructs. And now the question is, how do I actually use P and Q? So in the process calculus, I'm going to add a splicing rule. And all you have to know about this splicing rule is that if you look at U, it essentially matches what my process is currently looking for in the process typing in the conclusion. You have a few things like sigma and rho, which are essentially just substitutions that map the environments. But for intuition purposes, you can just ignore the substitutions and just say that like the contexts are equal. Okay? So now we can finish this example. I do the 2 let boxes on P and Q, bind them as code variables, and now I can actually use them inside the box. So I can programmatically compose processes and create more complex process code as I traverse my functional program. And so here's a, in quote, realistic example. Realistic because it solves a known problem. Quote, because it's terribly inefficient and pointless. But hopefully, I get the point of the concurrency across. I want to give a functional program, a function that takes in a number and then computes the nth Fibonacci number. Actually, I want to create a process that computes the nth Fibonacci number. Okay? So let's see how this looks. So here are the base cases. If n is 0 or 1, I return the trivial process that sends 1 and then closes. In the interesting case, I recur on n minus 1 and n minus 2, which will give me code, process code, right, that promises to send the n minus 1 and the n minus 2 Fibonacci numbers. And then I'm going to create this giant box. Here's the idea. I spawn P and Q, assign them to channels A and B, and then I receive numbers from them. So X would correspond to the n minus 1 Fibonacci number. Y would correspond to the n minus 2 Fibonacci number. I wait I let them terminate, and then I send their sum. Okay? So this essentially gives you a function that creates a process that concurrently computes the nth Fibonacci number. And if you have a more interesting or useful concurrent algorithm, then you can kind of imagine how this functional program might be able to build this process code and actually meaningfully use it. But one thing I need to answer is we've created the process, but we need to actually run the process. Otherwise, this seems not so useful. And this is a bit of a challenge. So the principle I want to follow is if I run a process which has a series of communications it can perform, I'm going to perform one round of communication as the functional program. And as for the rest, I'll capture it as some continuation or some reference. That's the idea. Here are a few other observations. I can only run processes that are closed with respect to the channel context. Why? Because my functional programming language has no concept of channels, no linearity. Okay? And I need to interpret each session type, which encodes the protocol, right, as some functional value, so I can actually meaningfully interpret it from my functional language. Okay, so here's the simplest case. Suppose I have this M, which is a process of type 1. Basically, it's a process that terminates. The only meaningful information I get out of running it is that I can observe that it closes. So this is kind of like a unit elimination because I don't really get information. Okay? And I suppose one more thing to mention, sorry. The sigma is just a mapping, so you can ignore it. All it does is it maps functional context. And M is, as I mentioned, the process code of type 1, so it will terminate, and that's the only meaningful behavior I can get out of it. Okay. The next more interesting one is if I'm running a process of type tau and A, okay? And here I want to focus on this X and this U. You see, when I run this, I'm binding two things. X, which is the tau, the thing I receive, and U is some process code of type A. So you can think of that as a reference. So if I ever want to run the remaining part of the process and communicate with it, I can use U to run that. Okay? And there's also implication, which is quite interesting. There are many ways, actually, to do it, but I wanted to keep run sort of a uniform syntax. So the way I do it is if I run a process of type tau implies A, which is a process that receives some value of type tau, then all I'm going to do is I'm going to defer the communication. I'm going to bind this U that's open with respect to X. So anytime I actually want to run in the future, I have to actually give a substitution for X, which essentially corresponds to communication in this case. Okay? And so the summary is that we have all these session types, and there seems to be a way to interpret it as a functional type. So this 1, the type that closes, is just a unit, no information. The type tau and A, sorry, is a pair of the value I'm receiving, the tau, and a reference to a process that eventually communicates on the session type A. And this tau implies A is a reference to a process that communicates A, but it has one open functional assumption that I need to actually pass on if I want to keep running it. Okay? So now we can take our Fibonacci process and create a Fibonacci function. All I'm doing is I'm running the result of that genfib, the function that computes a big process. Okay? And now this X corresponds to the number I receive. P prime corresponds to the rest of the Fibonacci process, which is just going to terminate. So I might as well just ignore it. Nothing wrong with running that again, though, and just letting it finish. Okay. So as a recap, I introduced sort of the ideas of fuses. And I sort of view it as a foundational work that combines functional and session-typed concurrency. And the key trick is first-class code. So I talked about code generation, and code execution. So, in the presentation, I talked about code generation and code execution. The idea with the generation is it's a contextual box that's sort of generalized to support linearity. And then the code execution occurs by interpreting each session type as a functional type and also realizing that the channel context has to be closed. I have to restrict what kind of things I can run. So in the rest of the paper, you'll see a lot of technical detail on code analysis through pattern matching. That's actually quite non-trivial because you have to deal with first-class linear context. So as you traverse terms, you have to deal with assigning meta variables for context splits. We prove type preservation, and we talk about our implementation and some sort of examples of code optimization that one can do with this kind of framework. Thank you very much. Any questions?
Right. So there's an important part I have probably missed. How do you guarantee the linear usage of channels?
The linear usage of channels is guaranteed by the process typing. So when I capture the process through the box, I make sure to type check the underlying process code using whatever session type judgments exist. So it's all static.
Familiar with process calculus, so this is my understanding, and this may be wrong, but it looked like your typing of sessions means that processes can only send a finite number of messages because they have the explicit with A. So I guess, is that a limitation of the type system? Or?
Typically in the session type system, you then add recursion to it, so you can handle infinite messages or arbitrary long messages. In this case, we don't have recursion on the session layer, but we do have recursion on the functional layer. So sort of like the Fibonacci example, what you can do is you can iterate and continuously generate code that has an arbitrarily long session. But I do think it's interesting to think about recursion specifically in the process layer in this kind of system. Thank you.
I wondered if you could say a little bit about sort of what the implementation, or I guess like runtime behavior here looks like, because you talked about how like in the functional code, when you run a program that produces some value, you sort of get a pair of that value and like the rest of the code. When the functional code is in that state, should I think of that code as being sort of like suspended at that point, or is it like entirely stopped and restarted when I run it? Because you also said at the end that like with the Fibonacci example, like you know that the rest of the program is just going to terminate, so it doesn't matter whether you run it or not. Is there some notion of like running it to like clean up resources, or does everything like completely stop when you go back and forth?
So this is something that's intentionally sort of kept ambiguous in the paper. So the implementation detail may vary, but here are a few ideas. And in fact, in my implementation, it's all code, so it's very inefficient. What will happen is that every time there's a communication, the functional program will signal the concurrent language to wrap up and then terminate every single sub-children you have, or pause every single children you have, and then return a code representation. This is necessary if you want to ensure that your code can be used for metaprogramming purposes, like you need to pattern match on the code later, or you need to duplicate it. But in like common examples, I've noticed that typically you just take that reference, you run it again. And in that case, I can totally envision a compiler optimization that detects this kind of linear usage of the process, the sub-processes. In that case, all you do is you really store a reference. You just keep that process running, and that seems fine. And you probably need some kind of garbage collection at the very end if you do detect that the process is not being run to completion.
Like based on how you actually write your code, whether you use the like pattern matching features or not, the compiler would like decide whether you can do the fast thing and keep it running or not.
Yeah, that's how I envision like a real implementation of this kind of system.
Okay. Thanks.
Hello. Jun Young from Maker University. So I have a question about your primitive for first class code. Is there any reason to use the wrap box system instead of a quote-unquote system?
So there were a few technical reasons that I don't quite remember. But I think one of the advantages with the box unbox is that it lets you keep nesting. So you can sort of talk about code that generates code that generates code and stuff of that nature. And one limitation of the let box is that you can't do that because it forces you to resolve all the code splicing at the top level. But personally, I felt that downside doesn't really appear in like typical examples. You don't really think about writing code that generates code that generates code. So the let box seems to simplify the meta theory and also the theory itself. So this is why we chose that. I do think an unbox is possible.
Thank you for the talk. So I'm curious. So the interesting point to me was that lifting session types to functional types. But so here I'm curious if the process calculus supports higher order channels. So I mean, so sending channels by channel.
Yeah.
Does it support it?
In the paper, I talk about extending the session type to support the tensor, a type which corresponds to high order channel transmission. And essentially, the functional interpretation is you just get a pair of code, right? We don't distinguish between, because we don't have a notion of linearity. It sort of exactly corresponds to the embedding of linear logic, or the correspondence between intuitionistic logic and linear logic. You just got to collapse tensor and,
All right, let's take '25 again. All right, up next, Haley is
Hi, can you hear me? Yep. So I want to start with a probability question based on real-life events. I'm currently trying to apply to 2 different companies for a research internship, and each company independently has a probability of 3/4 of giving me an offer, so 1/4 of rejecting me. And I'm just curious to know what's the probability that I would not have a single internship offer. So each company is independent, and so the answer is 1/16. You multiply 1/4 by 1/4. And we can model this with a sequential stateful program as so. Here, I create a reference that points to 0, and I perform a biased coin flip with the primitive coin p. So here I set p to be 3/4, and coin p basically is a primitive in the language that returns 1 with probability p and 0 with probability 1 minus p. I read from the reference, and then I store the value that I sampled back to the reference, and I do that procedure twice. And by the end, when I read the reference, that represents the number of internship offers I actually get. And so the assertion at the end will fail if both coins return 0 in the case and that's the case where the reference will be storing 0. So I might ask, for this program, what is the probability that this program crashes with probability at most 1/16? And that only happens when the assertion actually fails. To show this claim, we can use a logic that was presented at last year's ICFP called ERIS. And ERIS is a high-order separation logic for reasoning about error bounds of sequential probabilistic programs. And the key idea of ERIS is that we internalize probabilistic error as a separation logic resource, which we call error credit. And an error credit is written in this form, and this assertion, this epsilon is a real number that ranges from 0 to 1. And if you own this kind of assertion, owning epsilon error credit, intuitively, you're trying to prove that the goal is true with an error of at most epsilon. And you can see this intuition a bit more precisely from the adequacy theorem of ERIS, where if you're able to prove the Hoare triple on the left with epsilon error credit to start with in the precondition, then when you run the program, the probability that you get a value from the program that is not in the postcondition, or what we consider an error result, is upper bounded by epsilon. There are only 3 rules you need to know to use error credit properly. You can split error credit by summing them. If you have one error credit to start with, you can prove any postcondition. And this is somewhat intuitive because from the adequacy theorem, if you own one error credit, you're trying to prove that the mass of some distribution is upper bounded by 1, which is true for any probability distribution. But the most interesting rule for error credit is what happens when it interacts with the random sampling operation, in particular when we perform a bias coin flip. If we have epsilon error credit to start with, you can choose any epsilon 1 and epsilon 0 such that its expected mean is smaller or equals to epsilon, then whatever value n you get from this coin flip will get exactly epsilon n error credit. And this is nicely illustrated by the diagram on the right. It's also somewhat important to emphasize that this is a separation logic. So there might be more resources around the precondition and postcondition that might be framed out using the normal frame rule in separation logic. So with error credits, let's see how we can use these rules to prove our claim that the program actually the probability that the program crashes is at most 1/16. And to do so, we can apply adequacy, and it suffices to prove the Hall triple on the left. And the postcondition is true here because the only time the whole thing runs is if the assertion goes through. So now with the Hall triple on the left, let us symbolically step through the proof, allocating the reference, coming to the first coin flip. Here, with 1/16 error credit, we choose to supply 0 error credit if we sample 1, and 1/4 error credit if we sample a 0. It's somewhat interesting to emphasize that we're able to amplify error credit for some particular branches, and this is going to be useful at the end of the proof. We perform a case split on the value of x, and the interesting case is when x is equals to 0. So let's continue with that. So we have 1/4 error credit. We continue stepping through the proof, coming to the second coin flip. And here, we apply the same rule again, where we split error credits, but in a slightly different way, where we supply 0 error credits if we sample 1, and 1 error credit if we do sample 0. Again, as before, we apply case splits on the value of x. And if we do sample 0 here, we actually have 1 error credit, and we can prove any postcondition. So that case is solved. For any of the other cases, if we do continue step through the proof, for example, in the previous case where we do sample 1, at the end, the reference will be storing a positive number, and the assertion will go through, and that concludes the proof. So that's all nice. With errors, we can now reason about error bounds of sequential probabilistic programs. But that's not the end of the story, because this is a session on concurrency, and nobody in their right minds apply for internships sequentially. So let's rewrite a program to use a bit of concurrency, where now we use the parallel composition operator to split the interesting component. And we also modify the program a little bit to use the fetch and atomic add instruction that reads from the reference and increments the reference with a value x in 1 atomic step. Now, looking at this program, the behavior of this program is pretty much the same as before, and so we might want to prove the same error bound. But we can't do it with errors, because now we're in a concurrent language. And so we need something stronger. And here we introduce Canaris, which is a concurrent separation logic that inherits the ideas of error credit for reasoning about error bounds of concurrent probabilistic programs. And the good news is that all the rules from errors for error credit reasoning and the standard rules from normal concurrent separation logic are exactly the same in our logic. And it should be mentioned that although this is quite nice, this does not fall through directly. The model of Canaris is somewhat different from all the other previous logic, and we have to prove these rules from scratch one at a time. as mentioned, now we're in a concurrent language. We have to extend the operational semantics to reason about a concurrent thread pool, and we decide which thread to step through a scheduler. And so the adequacy theorem is modified to quantify over all possible schedulers, which might be stateful and probabilistic. So now with this Canaris, let's try to use Canaris to reason about our concurrent probabilistic program. Again, we apply adequacy. So it suffices to prove the similar looking Hall triple on the left. We step through the proof symbolically, coming to the interesting part of the program, the parallel composition operator. And we might just want to apply the normal rule for parallel composition. But there are two issues. Firstly, we need to know how we can share the reference resource, because both threads will modify and read the reference. But also, we don't really know how we're going to split the error credits, because if we split it naively into a half and supply 1/32 for each branch, or each thread, that is not enough for any of the thread to actually avoid sampling 0. And the key idea is to use invariance, which is a logical facility from concurrent separation logics that allow us to share resources between threads. And we support the familiar-looking rule from many concurrent separation logics, where if the expression is atomic, meaning that the expression will step to a value in one single step, we can open the invariant and temporarily access the resource in it from the precondition, and we just have to reestablish the invariance at the end of the atomic step. And again, even though this is the standard rule from concurrent separation logic, we still have to prove this again from scratch, because the model of Canaris is very different from other models. And the key idea now is that now we have invariance, we will store both the error credits and the reference resource in an invariant to describe how it changes. And here is a very high-level intuition of what the invariant looks like. And intuitively, the invariant encodes a state transition system. It stores three things. It stores the error credit, it stores the reference resource, and it also describes how the value of the value stored in the reference and the error credit changes with what the thread sampled. And these arrows represent the value that is sampled by the coin flips, regardless of which one goes first. So for example, in the case where both coins do sample 0, it goes all the way to the state where we have one error credit, and then that allows us to prove any postcondition. So with all the power of invariance from concurrent separation logic, Canaris allows us to reason about error bounds of now concurrent probabilistic programs. But in real life, when we verify programs, a lot of the times, the software is pretty big, and it's very hard to verify everything in one single pass. What we want is that we want to be able to prove specifications in a modular way. Let me be a bit more specific with this example, as an example. Here we have, this is the concurrent program we saw before, and we can split it into two halves, a module side and a client side. On the module side, we implement a concurrent randomized counter module that exposes three functions. You can create the counter, you can read from the counter, and you can increment the counter with a number based on the number of a biased coin flip. And now the client is modified to use the API provided by this module. Now the question is, can we provide a nice specification for the module that allows us to reason about the error bound of the client without having to know how the module is implemented? And this is a relatively tricky question. And the main problem with this kind of modularity is boiled down to how we interact with invariants. Previously, when we are reasoning about the client code, we have to access resources in the invariants. We have to do it once for the bias coin flip when we modify the error credits while going through the state transitions system. And we also have to do it another time for the fetch and atomic add instruction where we might need to modify the reference resource. But the only rule I just told you that allows you to modify and access resource in the invariant is this rule, where we have to know that the expression is atomic. But now we're trying to hide the implementation. And so the specification of the module should be somewhat expressive enough to enable us to actually access resources in the invariants. And in this particular case, we have to do it twice. To solve this problem, we can take a step back and ask ourselves, how do we traditionally prove the correctness of concurrent data structures? And a standard notion of correctness for concurrent data structure is the notion of linearizability, which intuitively is the idea that all the interesting operations appear to take place at one single atomic step, which we call a linearization point. In concurrent separation logic, we try to capture this notion of linearizability through logical atomicity. And it allows us to reason as if the data structure has that linear, modifies the interesting state in one single point in time. And in iris logics, like in iris logics, this kind of notion is captured through something called HOCAP specifications. The key idea of HOCAP specifications is that we parameterize preconditions with these view shifts written with this fancy update modality. And these fancy updates are also the logical facility that enables us to open invariants very flexibly. However, this is still not enough for our problem, especially when we have error credits and probability in the mixture as well. To explain why this is not enough, consider different implementations of the randomized counter module. This is the implementation you saw before for incrementing the counter, where we throw a bias coin flip to perform the sampling. But we can also do something a bit more strange, where we, instead of throwing a bias coin flip of 3/4, we can just simulate that with a fair coin, and we toss it twice. And we only sample one if both coin flips actually get a 1. I can also do something a bit more funky, where I implement the interesting random sampling with a rejection sampler, where I keep on generating a 3-bit number until I get something from below 4, and depending on the value between 0 to 3, I decide whether to sample 1 or 0. And the key idea is that even though all 3 implementations behave the same, the randomness operations do not happen in one single step. In other words, they're not atomic. But from the outside observer, they are logically atomic. And this is very strange, because for these operations, the number of times you might modify error credits is not like the modification of error credits might happen over multiple steps. But we want to reason about them as if we're all able to modify error credits in one single linearization point. And it's a bit challenging to figure out how we can condense the randomness into one single point in time and provide a specification that is satisfied by all 3 implementations. And the key idea is that we need to capture something called randomized logical atomicity, which intuitively describes how modules can commit to some future probabilistic choice in a logically atomic manner. And in Canaris specifically, we captured this notion through a probabilistic update modality, which is somewhat similar to the fancy updates you saw before, but it also allows you to update error credits. To demonstrate that this approach is very flexible, we provided a lot of case studies, including this one, where we implemented a thread-safe idealized hash function. we model the hash function as a random oracle, meaning every time we hash a key we haven't hashed before, we choose a random number to be the final hash. And it's also thread safe in the sense that if it's shared by concurrent threads and both threads hash the same key, they should be mapping to the same value at the end. We provide a flexible specification where if you initialize the hash, you will get a hash key abstract predicate for every key in the domain of the hash. And this hash key predicate represents the knowledge inside the hash. It represents what kind of keys, what kind of values are mapped to from each key. And initially, all of these hash keys are uninitialized because we don't have no knowledge of what each key will map to. And you can pre-sample and decide which key it will sample to through a probabilistic update modality. And we have a very flexible way of also splitting error credit depending on the value a particular key is mapped to. Finally, if we do have the knowledge that a particular key is hashed to some value v, and when we do run the program where we apply the hash function on the key, we'll get that particular value back. To show that this specification is expressive and useful, we implemented a concurrent Bloom filter using this specification. And we're also able to prove tight bounds on the probability of getting a false positive. And it should be mentioned that, to the best of our knowledge, this is a new result because the proof of this requires the reasoning about the intersection of probability, concurrency, and local state. In conclusion, Canaris is a separation logic that enables us to reason about error bounds of concurrent probabilistic programs by inheriting the rules of error credits and rules for reasoning about concurrency from concurrent separation logics. In addition, we can do so in a modular way by capturing randomized logical atomicity with the probabilistic update modality. There are more things in the paper. For example, details of the specifications and the proofs all presented in this talk. And also, there are also more convincing examples. For example, a lazy sampler and a concurrent amortized collision-free hash, which is inspired by a similar example from the original Eris paper. I thank you all, and I welcome any questions. If you do have any research internship opportunity and you find this kind of research very interesting, I'll be here for the next few days, so do look for me. And my advisor, Lars, is also recruiting any interns, PhD students, and postdocs. If this research seems very interesting to you, I'm happy to chat with you about my experiences in Aarhus. With that, thank you all.
How hard is it actually to find those proofs? Like now you have the formalism. How hard is it to actually prove anything?
A lot of the rules, so for example, the one where I showed you where you have the concurrent probabilistic program where, like the new modification, like this one, like even though the invariant the invariant matches a lot of the other proofs in just normal concurrent separation logic. So the way we encode this invariant is just very standard, using ghost resources and just normal, it's kind of somewhat intuitive as previous concurrent separation logics that don't have probability. So we argue that it's actually not too bad, and it's, if you understand normal separation logic, this one goes through pretty nicely. My intuition, so I think I don't really agree with the notion that the error credit is always decreasing, because although it is the case that you can spend error credits as you go through, with the sampling rule, you can actually amplify the error credits for some particular branches. So in that case, I think the idea of monotonicity is not exactly the same as what's in how we use error credits. Yes.
Thank you very much. Let's thank Haley again.
Can everybody hear me? I feel like I'm not very loud. Everybody in the back? Everybody? Yeah? Thumbs up? Thank you. What if I talk a little bit? Okay, it's not gonna. Let's see. Ba-ba-ba. Do I have to? There we go. Okay. Hi, everybody. Okay, everybody can hear me okay? So this talk is, so I'm assuming everybody here is already a fan of functional programming, but maybe you guys don't know a lot about distributed systems. There is a lot of overlap between these two areas with things like Hadoop MapReduce or distributed futures, but what I'm trying to do is expand the scope of functional programming so that you can take any distributed system and express it as a kind of functional program. And the way we're doing that is with something called choreographic programming. So to understand why we do that, let's take a look at a very simple example of a distributed program, the OpenID authorization protocol. The problem is you have to write 3 different programs to implement this protocol. You have to implement the authentication service, which will receive something, send something to the server. You have to implement a server protocol, which will receive something from the authenticator, and then it will send something to the client. And then you implement the client also, which what it's going to have to do is receive from the server and send to the authenticator. And so these 3 programs, you can see that they're very tightly coupled, right? And if I made a mistake in any one of them, the whole system goes down. And you'd be forgiven for not noticing that there's a bug in this program. There's actually a deadlock, because all 3 processes, they start by receiving. What I should have done was flip the order of those 2 different statements. So whenever I'm in a situation where I have an error-prone kind of domain that I'm programming, my first instinct is to say, I'm going to write a higher level language that compiles into that error-prone domain. And that's exactly the idea here. The high-level language, it's something called a choreography. And the concept of projection is how we compile it to generate that code. And if you're thinking that sounds a lot like Lynx, or it sounds a lot like Scala-Loci, or any of these other things, you'd be exactly right. But I'm going to try and convince you why choreographic programming is the nicest one, at least from the perspective of like a fan of the lambda calculus. So let's write this same authentication protocol, but using a choreographic programming language. But I'm going to start not with a choreographic language, but with a local language. So maybe Java or Haskell or whatever. This is just a sequential programming language. And the idea is, in this program, we're going to get the token from the client. We're going to check if the token is valid. If that token is valid, we're going to get a result. And then we're going to print the result. So this is a simple sequential program. We're acting as though all our 3 participants are in the same location. And now to make this language choreographic, we just add locations. So I've added these 3 location parameters, the client, the authenticator, and the server. And now I specify, whenever I invoke a procedure, I specify this procedure is executed by the client. This one is executed by the server. And whenever I have a piece of data, like this function is valid, I specify where that function is located. It's located at the authenticator. And so we almost have a complete choreographic program now. The only thing, oh, actually, I should mention one other thing. I'm not going to actually show types in this talk, but we also have to add locations to our types. So instead of just having a token, we have a token at the client. Instead of having a Boolean, we have a Boolean at the authenticator. So we almost have a choreographic program, but if we write this in a real language, we'd get a compilation error. The problem is that the isValid function is located at the authenticator, but the token is located at the client. So this is why we need to add an extra piece, which is these concepts, this thing called a communication. So this function over here, com from client to auth, you can think of it from a programming perspective as a type coercion. So it will coerce the token at the client into a token at the authenticator. But what it's actually going to do at runtime is send a message from the client to the authenticator. Pretty good. That's it. That's all we have to do. And so if you're not familiar with choreographic programming, it's important to kind of get a sense for how this actually compiles. So pay attention if you haven't seen this before. The idea is we're going to compile this program 3 times, once for each of the participants. For the client, we're going to look at all the code that's at the client, and we're going to generate the client code for that. You can see the 2 lines in the choreography, they match the 2 lines that we have in the generated code. And the 2 lines for the authenticator, we're going to generate 2 lines over here. And for the 4 lines or 5 lines over here, we generate 5 lines over here. There's a symmetry here. And the rest of the code that's not pertaining to that process, it disappears. So the nice thing about choreographic programming to me is that it takes global problems and it reduces them into local ones. So for example, checking if there's deadlock freedom, that would require an analysis between these different modules, right? But when you write it as a choreography, it becomes a very simple syntactic check. And if you want to check something like, are our messages well typed? It again becomes just Hindley-Milner on the left-hand side. So that's really nice. It's a really useful feature. And I haven't said any problems yet. Why am I giving this talk? The problem is that when it comes to higher order models of choreographic programming, we actually don't agree on what the semantics should be. So there's going to be 3 competitors in this talk. One is Coral, which is a choreographic programming language based on Java. There's also the Core Lambda family of formal models, and there's the Pirouette family of formal models. And the problem is that they don't agree on various programs. So for this Coral program at the top, don't look at it too carefully. The point is it's a program. It's not even valid. It's pseudocode. The point is that Coral will, when you run it, it'll print hello. And Core Lambda says it'll print hello. But when you embed this program into Pirouette, it won't do anything. And if you take this program, it prints hello in Coral, but it actually shouldn't, according to these 2 models, it doesn't have any effects. So what's going on? Who do we trust, right? And also, why do we care? Well, like, let's say, I should mention this. Like, let's say that I've convinced you guys that choreographic programming is super duper cool. Maybe you want to take one of these papers that you see at ICFP, maybe like there's a new type system, and you say, oh, I can make it a distributed type system by applying it to choreographic programming. Well, so you probably want to implement it in Coral, and you probably want to prove the type system is safe in a formal model. But our formal models, they don't match our programming languages. So that's a bad thing. And also, if you're a programmer who's using choreographic programming, it means that you might be refactoring your code, inlining stuff, extracting something out into a separate definition, and then unknowingly, you change the semantics of your program. And optimization as well, it uses inlining and expansion. And in a compiler like Haskell or OCaml, they basically use a beta rule for a lot of their optimizations. The problem is we don't agree on what the beta rule should even be for choreographic programming. So if we want to make an optimizing compiler, we need to figure this type of stuff out. So let's get at the heart of the problem. When you're doing choreographic programming, you have 3 different pieces, and they all need to fit together perfectly. You have the semantics of your target programming language, which might be something like OCaml, Haskell, Java, whatever. And we have the semantics of the choreographic language. And we have the projection function that compiles the choreographies into whatever our target code is. And the projection theorem is something that tells us how these things are supposed to relate to one another. It's essentially going to be a bisimulation between the semantics of the choreography and the semantics of its projection. And so Pirouette's approach is to start from the local semantics and say, well, I know that this is going to compile to Java, so it's call by value. And the choreographic semantics, well, it should probably be called by value too, but plus some like extra concurrency or something. The problem that they found is that when you take these 2 assumptions, the projection function has to have global synchronization whenever you invoke a choreography. And so that's when you have a lot of choreographic compilers like Coral, they don't have this global synchronization. So that's why there's a mismatch between Pirouette's semantics and Coral's semantics. Now, I talked about this other formal model, which is called Core Lambda. And what Core Lambda did is it started with, again, a call by value local language. And it started from an assumption of what the projection function should be. And then we tried to solve for x. And what we found is something really weird. We found, for some reason, there was evaluation underneath lambda abstractions. Like, you could run effects underneath a lambda abstraction. And that's like, why is that safe? I don't understand. I don't know how to reason about that. And you also have these weird commuting conversion rules. Don't look at this too hard, but I hope it looks complicated. And so we kind of, we have these really strange features in the semantics. And what we're trying to do is we're trying to find, a perfect union of choreographic programming and functional programming. But I'm afraid that it comes across to functional programmers more like a serial killer wearing his victim's skin. Like we're just kind of appropriating the lambda calculus to publish papers. But what I'm going to it's the first one. It's the first one. I'm going to show you. But we have to kind of do a little bit of work. So what I'm going to do in this talk is start again from where core lambda started, but we're going to try and clean up the choreographic semantics. We're going to try and look at other work and see if we can contextualize all those weird features that we saw and maybe make them a little bit less scary. So how do you define an operational semantics? Well, what I like to do is I define my redx's, and I define my evaluation strategy, the order that I evaluate those redx's. So let's start with a very simple choreographic language and figure out what are our redx's. Do they look scary? Well, fortunately not. For example, if we have an if expression in a choreographic language, it's if true m1, m2, it just evaluates to m1. If it's false, it evaluates to m2. And the communication function, it's not too complicated either. It just takes a constant that's located at A and it maps it into a constant at B. Let bindings are how you would expect. They take a value and it substitutes the value into the body. And lambda application, I'm going to do something slightly weird, but hopefully not too scary. I'm going to, instead of just reducing this into substituting n into the body of m, instead what I'm going to do is I'm going to reduce that into a let binding. So hopefully that's not too scary, but we're just splitting it into two steps. Instead of just substituting, we put it into a let binding first. So now that we have our kind of atomic notion of computation, what order do we do things in? This is where it starts to get really interesting. And so just as like a thought experiment, let's say that we gave it like a classic traditional OCaml deterministic call by value evaluation strategy. What would that look like, and how does that compare to what we actually want to have in real language? So this is our evaluation context in that case. Hopefully it's not too scary. You've got it basically says you want to evaluate the thing on the left, and then you evaluate the thing on the right in an application. If you have an if expression, you evaluate the scrutiny. If you have a let expression, you want to evaluate the thing in the binding. Very, very straightforward. And so let's take this choreographic program and assume that I have this semantics. Can somebody tell me what it's going to evaluate first? Seriously, like, I have time's up. Like, quickly, somebody, anybody. Oh, come on. OK, it should be an in right here. Yeah, it should be let in, let in.
OK. And then that print at A has two arguments?
It's just one argument. It's the world constant that's at A. Yeah.
Or maybe it's hello at A and print at A.
Let's see. It's print hello at A, print at B the foo, and then print A world A. So it says print at A prints something, B prints something, A prints something. Is that good? I got to have Simon know like what I'm doing.
Yeah, I'm still parsing.
Still parsing? Oh, gosh.
Does at bind more tightly than application? Yes.
Yes.
Oh,
yeah. Yeah, so this is like a constant at A. It's a print constant at A. Okay. And this is a hello constant at A.
Oh, OK. Thank you. OK, parsing over. Right.
OK, good. If you guys weren't parsing this stuff, the rest of the talk is going to be completely worthless. So who can tell me what it's going to do first? Actually, Simon, can you tell me what? Anybody? Yeah, it's going to print hello at A, exactly. And the way we do that is we split this up into an evaluation context. This is the context, and this is the redx that we're going to evaluate. Great job, everybody. That was longer than I expected, but I think we did a good job. And so when we have this kind of evaluation strategy, one of the features is it's deterministic. There's only at most one way to decompose it as an evaluation context and a redx. And so this means that it's always going to print these things in the same order. That's expected. That's what OCaml does. But what does it actually do if we compile it with Coral? Well, we look at all the code at A, and we're going to generate this code at A. And we look at all the code at B, and we generate this code at B. And these two processes are going to execute concurrently with one another. So what can this do? I'm not going to wait. What it's going to do is it can print, you can have A print hello, then B prints foo, and then A prints world. Or you can have A go ahead and do everything, and then B prints foo. Or you can have B be the one who runs first, and then A finishes. So there's 3 different executions that we need to be able to do, so we can't have a deterministic evaluation strategy. It needs to be able to choose different stuff. So number 1, our rewrites have to be non-deterministic. And number 2, our rewrites have to be able to evaluate underneath a let binding, right? Because we need to be able to execute this foo. So, but that's not too scary, because does anybody know a great programming language that allows you to evaluate the body before the binding? Haskell, yes, call by need, exactly. So it's not too weird. And there's a close cousin of that call by need evaluation strategy, which is called lenient evaluation, lenient semantics. And what this allows you to do is not just, it allows you to evaluate the binder and the body concurrently with one another. And to get a lenient semantics, it's very straightforward. I mean, I'm going to simplify a little bit, but essentially we just need to add one thing to our evaluation context. We add the ability to evaluate underneath the body before a binding. And so if you take this original choreography now and we give it this semantics, what's it able to do? Well, we can decompose it like this, or we can decompose it like this now, or we can decompose it like this. So now we can execute different things. So we can get all 3 of the different executions that we wanted to have. But the problem is that now we've given a little bit too much concurrency. Now we can actually evaluate this world before this hello. So the correct solution is we want to have the rewrites be deterministic for each process. So A prints hello before it prints world. But we want concurrency between different processes. So there's no evaluation strategy we know of that gives us this, but so we just coined the term. It's going to be called semi-lenient. And it's just a very small, very simple addition to the lenient, which is to add this extra side condition. So to write it, what we do is we take that lenient evaluation context from before, and we index them by processes. So there's an evaluation context for each process. And the other thing that we do is we specify the process P can evaluate underneath the binding if it's not involved in that binding M. That's all we have to do. And so this is the explanation for that weird evaluation under lambda that we had before. Why were you able to do it? It's because really that's trying to capture the fact that you can evaluate underneath a let binding sometimes. So it's a little bit less scary. But if that was all that we were doing in this work, I don't think it would be worth looking at. But what I think it gets us is an ability to start to see connections between choreographies and other lambda calculi type models. In particular, let's try and apply some other ideas from other papers to understand the commuting conversions, these scary things that we needed in our semantics. So let's see where those commuting conversions come from. Here's a choreographic program where it's an application of the left term to the right term. And the left term says A is going to do an infinite loop. And then this program returns print at B. And on the right-hand side, we have a string hello at B. So we're applying the left-hand side to the right-hand side. And when you compile it, you take all the code at A, and you get an infinite loop at A. And you take all the code at B, and you get the print applied to the hello. So process B, it can apply the print directly to the hello without even doing an infinite loop. So this means that the local code is able to print hello without even waiting for process A. But with the choreography semantics that I gave you so far, you're not able to do this because you'll never be able to find a regex that matches that print to that hello. That's the issue. So to make this work, we have to add a rule to our semantics. We have to be able to push that M prime into the let binding. And that's fine. Maybe we get an extra rule. That's not so bad. But now you have this program. And now, if you get the exact same projection again. B is able to print, but our semantics isn't able to do anything. So we have to add another rule. Now we can push the V in from the left-hand side. And this process repeats over and over again. You keep trying to prove the projection theorem, and you find it doesn't work, so you have to add a rule to the semantics. Then you do it again and again, and hopefully you didn't make any mistakes in the proof that will cause you to miss any of these rules. And this is for like a simple core model. If we're trying to do like a real big compiler, forget about it. So fortunately, there's been a lot of work that touches on commuting conversions. You can see it in call by need. You can see it in call by value when you're doing stuff that I don't understand, honestly. And you can see it in some lenient programming languages. But what we're going to talk about is specific work over here that was looking at optimizing Haskell compilers. Now, they didn't have commuting conversions in their semantics. They were using it as an optimization. But we're able to actually lift some of these great ideas that they had there and apply them to choreographies. Specifically, the beautiful thing that they did was they took this evaluation context idea and they broke it up into 3 parts. You've got frames over here, which are the parts of the evaluation context that consume a value. And you've got answering contexts, which are the part that produce values, sort of, intuitively. And all you have to do to get all your different commuting conversions is say this one rule over here. You push a frame into an answering context. And that's going to generate, if you inline the definitions of F and A, it's going to generate all these rules on the right-hand side. I've actually shortened I haven't included this select notation. So this is actually from the real paper. We generate 8 different rules with this one simple rule. And so this is the really cool part, because we start to get context for these rules that were showing up in previous choreography models. So these first 2 rules over here, we see them in call by need. That's really interesting. These other 2, they came up in that call by value paper that I talked about. These rules, they all show up in core lambda. That's really, really nice. And this rule, it's actually a much simpler version of the one that we had in core lambda. The one in core lambda has this weird side condition with the synchronizing processes. We managed to simplify it over here because instead of having an arbitrary term m prime, it's a value. And we wouldn't have had that insight that we could just use a value instead of this side condition without this type of approach. So the rules get simplified, but also these 3 rules, I said they didn't show up in core lambda. Why is that? It's because they were missing. It's because the proof, there were these very specific edge cases in the proof, and we overlooked them. So this is like a really nice idea where we managed to apply theory to practice and discover something new. So to wrap up, the semantics of choreographies we found out isn't just some arbitrary thing that we bolted on as a result of the compiler. It's something that has a very close connection to strict and to lenient semantics. And we show in the paper that there's like a recipe that you can follow by starting from the semantics of a local language to build a choreographic programming language. And that recipe comes with laws like about your answering context and about your frames. So that's much nicer than the approach we had before, which is just, I don't know, try and prove this big by simulation result by induction. And it raises a lot of interesting questions. For example, I talked about the local semantics, the choreographic semantics. Well, if the choreographic semantics is extracted from the local semantics, what about the projection function? Can we kind of extract that too to some extent? We don't know. Does this work generalize? In the paper, we gave it a very small core calculus. And the interesting question is, how does this work with all the other features that people are adding to choreographic programming? We don't know. This is an interesting question. But I think the fact that we were able to discover stuff is good news. And the last question is, still to prove the projection theorem, it's a lot of work. So the question is, can we kind of automate this process to any extent? Can we mechanize it? That's a really interesting question. Lots of interesting questions in this area, and that's all from me. If you want to hear more about any of this type of stuff, you can go to my website. And I should mention that my podcast co-host Pedro is going full-time on the Type Theory for All podcast, so you can support him by buying a hat. Okay, thank you.
Ashley from UW-Madison. Jesus, that's loud. I had a question about what was on your last slide about generalizing to other features. In particular, I was curious about some of your side conditions in your paper involve reasoning about the processes in a certain step. So do you think this could generalize to process polymorphic languages?
You were talking about side conditions? You mean about the synchronizing processes? Yeah. But I really have kind of, it's a blind faith. I think it's just because the theory allowed us to discover new things, I think like this is probably a good theory. So if there are processes, if that's a useful thing in the world, if God thinks that that's a good thing to do, then I think that it should generalize. That's my faith.
Hi. You mentioned that some previous work was just missing cases, missing rules. Does that mean they claim to have proved things that weren't actually proved? And if they were missing cases, why are you confident that you aren't missing cases?
Yeah, who knows if we might have missed some cases. So it was proved by hand. So because of that, they just missed them. It was part of our group, unfortunately. But that's a testament to how difficult these types of things are, even for a very simple model. And we could have made mistakes. It's partially why I want to kind of automate this stuff. But this is the nice thing about great theories, is that we were able to follow this process and still discover stuff. So, if you combine this with mechanization, that would be even better, maybe. Actually, when I was giving those 8 rules, I only wrote out 7, and it had to be my co-author to point out, 2 times 4 is 8. There should be another rule. And we found out that one of these 3 missing rules. We added another missing rule, basically. Anyway.
Thank you.
Sorry.
Yes, it does.
Test. It's just way too loud.
We're going to make a start now. Good afternoon, everyone. Welcome to the session on types and specification. And our first talk is going to be about MUC-TT, a verified kernel for a proof assistant. So I think we're going to think about the question of should we trust proof assistants, which is a very important question. And Junyong Chang is going to lead us in the talk. Thank you.
Thank you for the introduction. This work, MUC-TT, is a collaborative work with the Anton Gaurin, Jason Hu, and Brigitte Pienka. And I'm gonna start with this thing. So nowadays, there is the increasing concerns of correctness of software systems. So Consort has been a decade thing, and there is the BAS-FS, which is a verified file system implementation. And there is Certicourse, which is the certified concurrent OS kernels. And there is some other industrial works to verify software systems. Well, popular way of get correctness of software system is using a proof assistant. But a proof assistant is also a specific kind of software system. So how should we, or why do we trust a proof assistant as a software? Common way to work around in this question is that providing a small kernel so that one can check whether that kernel is really correct and reflects the theory. Now the question is that, is it really small? It turns out Rook has now 41,000 lines of code for its kernel and suffers from 50,000 bugs since the 2040. And Lean, which has comparably smaller kernel but written in C++ and has been suffered from the soundness bug as well as segfault bugs since the 2020. And Agda does not even have kernel. So we need to deal with the entire 100,000 lines of code to trust Agda. And it has been suffered from 80 soundness bugs since 2015. So under this situation, why don't you just verify the kernel itself and providing a verified implementation for kernel? Another point of verified implementation is actually, verified implementation is not just about the correctness. We are not talking about verified theory. We want to have an extensible implementation in a sense that one can add more features to the verified implementation. Otherwise, it will be quickly become a meaningless thing. And the streamlined implementation in the sense that verified implementation should not carry any information about proofs. I mean, once verified, the verified implementation should not carry all the noises from proofs to be efficient. And it should be human readable so that readers can check whether the implemented algorithm is correct, not depending on our verification itself, but by reading the extracted code. And maintainer might want to test a feature candidate without fully verifying it because it is, after all, feature candidate and they might not want to implement after testing it. So here I present the MACTT, mechanized type theory, which consists of three parts. First, verified theory. We verify the core Martin-Löf type theory with cumulative universe hierarchy, inductive base type, and other extensions. Second, we verify the algorithm for type checking and normalization of MLTT, and shows that the soundness and completeness with regard to the theory. Finally, we provide the verified implementation, which is extracted from the verified algorithm part of ROC, and it is streamlined and human readable. All these things is verified in ROC proof persistent. So let's go into the actual overview of MACTT. MACTT starts from the stream of tokens, and parser converts it into a concrete syntax tree. And then our operator translates it into abstract syntax tree, and in backend, we evaluate the abstract syntax tree into a semantic domain and read back from there to normalize it. This is a technique called normalization by evaluation. And by depending on this normalization algorithm, we show that we provide the algorithmic components for typing and equivalence, basically conversion checking. And then we prove that this algorithmic component is sound and complete with regard to the syntactic typing and equivalence checking, equivalence judgment. After proving all these properties, we extract the ROC version into OCaml version. And then we add some string processors, Lexer and Pretty Printer in OCaml, so that we can get source code and Lexer in OCaml translated into a stream of tokens. And the stream of tokens goes through all the ROC things and actually into the extracted things, so that we can get the yes or no, basically the answer for the where typeness. So it says yes for the where type terms and no for ear type term. This entire system is implemented in 20,000 lines of code, and this includes the entire proofs. So excluding proofs, this is around the 10,000 lines of code. Key challenges in this implementation is two. One is encoding of induction recursion in ROC, and the other is algorithmic type checking with universes. Let's first talk about the encoding of induction recursion. However, before going into encoding of induction recursion, what is induction recursion? Induction recursion is something to do with something like this. So basically, suppose that we have this kind of function, and we want to formalize this within some proof persistent. However, this is not so easy because it's hard to say whether this function terminates or not. So before even proving termination, how can we actually encode this into a proof persistent? One easy way is providing a domain which allows us which plays the role of a termination measure for a function implementation and defines when the function terminates, and function definition that depends on that domain. So basically, when the first case, when the n is greater than 100, then it immediately terminates, so we don't need anything else. And the other case, where the function terminates only when the inner function and the outer function call both terminate, we first say that inner function terminates based on this domain definition, and then says that external function call terminates based on this domain definition. But note that here we use the function we are now currently defining. And in the function definition, we need to pattern match on P to actually define the function, because that's our termination measure. This kind of mutual dependency between inductive type definition and recursive type definition is possible only when we have induction recursion. So induction recursion is a feature that allows to define this kind of mutual definition. But where is induction recursion in our system? It's in normalization by evaluation part. More specifically, it happens when we want to define a semantic equivalent of equivalence rules, which is the evaluation result of equivalence. So this per model part is the problematic part. Why the per model introduces the induction recursion? So per model basically requires two parts. One is the relation or equivalence between types, and the other is a relation between terms. Relation between types is actually defined inductively while using relation between terms. And relation between terms is defined recursively by pattern matching on relation between types. So there is induction recursion because of this relation. Now question is that now the problem is that Rogue does not support induction recursion. So how can we encode induction recursion in Rogue? A common method is something called Bob-Capretta method, which is named after the Bob and Capretta. But this method does not work for universe hierarchy, full universe hierarchy. So we cannot use this method. And instead of that, we come up with the one key idea that we do not need to compute ER. This ER is used only for proofs, and we never use this ER in terms of algorithms, so we don't need to use ER we don't need to compute ER. Because of that, we can define a proof, we can prove propositions UI as a functional relation that returns ER. Like if we represent it in a judgmental form, it's like this. It says that A and A prime is related in universe I, and that universe I returns the elemental relation ER, which describes the term, the equivalent term in A and A prime. This solves our problem of induction recursion. However, it also gives us one more bonus. Like when we define the UI as a functional relation, should it really be functional relation? By functional, I mean output ER is unique. Should it really be unique? The answer is no. We don't need to be. It doesn't need to be unique because we don't care about what ER is. We only care about what ER relates. It is related to. We don't need to compute ER, and we only cares about what ER is actually for. So instead of the functional relation, we can use weakly functional relation. By weakly, I mean output ER is unique up to relational equivalence. By relational equivalence, they relate the same things. Advantage of this thing is that basically we can remove several direct applications of functional extensionality, and basically all applications of propositional extensionality in our proofs. Now, next, go into the next challenge, which is the algorithmic type checking with universes. I put spaces there because by algorithmic type checking, what I mean by is actually algorithmic bidirectional type checking. And let's go into the this kind of simple cumulative universe rule. Within this simple cumulative universe rule, we can type check this kind of example. A function that takes y and returns y, and y is in type 0. then the function type pi y in type 0 returns type 1 is where type because we can apply the cumulativity rule on variable y. If we add some more complex structures, like basically one beta radix around the original term, we can still type check as long as it is declarative type check. If we go into the bidirectional type checking setting, in usual bidirectional type checking setting, when we have functional application, function part will be inferred, and this is the inferred type in the inferred type for the function. However, the return type of the function, which we will get after application, doesn't match the type we want. The problem is that the return type of each function, type 1 and type 0 doesn't match, and there is no way to rip the function between type 0 and type 0 into type 0 and type 1. So we need to avoid simple cumulative universe. Instead, we use a roguelike covariance subtyping cumulativity. Basically, we have the subtyping rule and the cumulativity rule and covariant subtyping rule for function type. So if we go back to the same example, the function part still infers the same type, but after application, these two types are now in the subtyping relation, and by applying the subtyping rule, we can get the desired type. This kind of subtyping happens in general for all negative types, and we added this kind of subtyping rules for negative sigma type as well. There are basically two takeaways from these challenges. One for induction recursion, and the other for subtyping. And for induction recursion, the takeaway is that we can encode every induction recursion even when the recursive part, EL, is also in predictive universe. And the second one about subtyping is that our theory and algorithm should be developed together. So subtyping is added for algorithmic concern, and which was not there for the previous MRTT theory mechanization done by Jason Hu, myself, and Bridget Penka. So far, we are talking about the challenges in the MACTT, and let's go into the human readable streamlined part. So the upper part is the rogue definitions, basically just the type part, which describes the implementation for the subtyping checker. And this A and B is a normal form, and it returns either A and B is in a subtyping relation or not. And if we extract the entire code into OCaml, what you get is this kind of readable code. By readable, I mean what it does is like clear. When A and B is both the universe, we check its level is in order is less than order, and if both the type A and B are function type, we compare the input type with the equality, and the output type with the subtyping checker. Same happens for the general subtyping. Previously, it was for the normal form, and this one is for general subtyping. And for general subtyping, we return either A and B is in the subtyping relation or not. And extracted code is just like normalizing A, normalizing B, and compare it by normal form implementation. So conclusion is, MACTT's contribution has contributed to the as a first end-to-end verified kernel with the cumulativity, inductive base type. It has the streamlined type checkers and normalizer of cumulative type universe type theory. Encoding a pure universe hierarchy using imperative activity is like different from the Bob Capretta method, and we presented in here as well. And we also presented the design principle based on the interplay of type theory and implementation or algorithm. We basically have 2 lines of future work. One is for towards alternative or secondary kernel for Coq, Rin, or those kind of existing proof assistant. And for that, we have working on adding this kind of interesting type that can be used for the secondary kernel, propositional equality types, segment types, and user-defined inductive types. First 2 are already finished in our master branch, and the third one is currently ongoing project. And there is another part of the future work. We are envision this as a playground for verified type theories. So we are currently working on pure type systems type theory implemented on this framework. And we are also envisioning the modal type theory implementation, such as Cocon, based on current system. So far, this was my introduction to MacTT, and if you have any question, feel free to ask. Thank you for listening.
Excellent. Let's take some questions.
Thank you. So this kernel was verified in Rock, right? So in the end, we still have to trust Rock's kernel to trust this kernel.
Actually, one of the points why I mentioned I put the emphasis on the human readable part, because to distrust this system, you first need to distrust the code raw, and you need to distrust our declarative rules and proofs, and you need to say that destructive part, the problematic part in raw, should affect our proofs. And third, after reading the extracted code, you still say that this extracted code does not make sense because it might have some bug here and there. So like there are several layers of trust you need to break. So this one is more like adding a trust layer than like providing a complete unbreakable trust. Yeah.
Hopefully in the future we can bootstrap our trust.
More trust-based.
And we keep going,
Yeah.
So I have related questions. The first thing is that there's the LogRail project and paper that does very similar stuff.
Sorry?
The LogRail project. They have a paper at CVP called Martin Love à la coque.
Martin Love à la coque, I see.
So I don't know if what's the difference compared to what you're doing, because as a non-expert, it seems very similar to me.
Yeah, in Martin Love à la coque, the implementation is, there are basically say 3 main differences. The first one is that their implementation is based on something called the reducibility candidate, and our implementation is based on normalization by evaluation. Normalization by evaluation is known to faster for success case and slower for failure case. And as I said, we envision this as a secondary kernel for the proof assistant. So we don't need to care about, we less care about the failure case, because failure case means that the proof assistant, the first kernel has a bug. So we less care about that kind of case. And their system does not have extraction, or like they have extraction, but only the fewer extraction. By fewer, they can take a finite number of steps, and our extraction proves the termination and does not need to depend on the field extraction. And third, final one is that our system has a cumulative universe, so we need to use the proof, the impredictive universe for to encode the induction recursion, but their system does not require the induction recursion at all because their system does not depend on the full universe hierarchy. They just have two universe, basically the types and the terms. Yeah.
So compared to the MetaRock project, I understand the difference is that you prove consistency, but to the cost of not having prop. Compared to the MetaRock project, you prove consistency, but you don't have prop because of that. Okay.
All right, let's thank our speaker again. Yep. Okay, so the next talk of this session is going to be remote. It's about linear types with dynamic multiplicities in dependent type theory. So we've got a whole bunch of cool stuff coming together there. It's a functional Perl given by Maximilian Doré, who will hopefully be appearing on our screen very soon.
Hello. There we are. Perfect. Hope you can hear me well.
Yes, we can hear.
Okay, I'll get started.
Yeah, go ahead. Thank you.
You can see that I'm streaming, and I'll hopefully also be audible. Yeah, I'm very sad that I can't be with you in Singapore, and I'm also very sorry that you now have to sit through a remote talk just after lunch break. I know it can be hard to pay attention to a talk delivered remotely, so I'll try to lighten things up a bit by having some pictures somewhere along the line. But let's get started. In this talk, as Dominic already said, it's going to be about linear types. And linear types are inspired by linear logic. If you haven't come across linear logic, in a nutshell, it's a restriction of classical logic where we treat variables as resources and we can't just duplicate or discard resources freely. So in linear logic, these two functions are actually not tautologies. So we write this OX or tensor for AND in linear logic. So A and B does in fact not imply A. So this lollipop symbol here is the implication of linear logic. And similarly, we can't just copy the given A. So we don't have a function taking A to A and A. And linear logic is very useful in programming because if we, under the propositions as types interpretation, look at programs in a linear type system, then they have to be tautologies of linear logic, which in the case of a function between two lists means that any function, any linear function of this type has to be in fact just permuting the list because we can't drop any elements of this list or we can't duplicate any elements in this list. And hence, we already have actually a quite strong property satisfied if this is a program in a linear type system. If you've ever shown a sorting algorithm correct, I think you know that it's quite tricky, or the trickiest part is actually to show precisely this, that your sorting function is just a permutation. So this comes for free as a specification in a linear type system. A very natural extension then to linear logic is to still allow in a restricted way copying if we explicitly annotate it. So there's this idea of introducing a multiplicity, which will, kind of in the spirit of linear logic, ensure that, or like a type system will ensure that any program where a variable has a given multiplicity, this variable is used exactly as many times as the multiplicity says. So for instance, if we have here the copying function, we can indeed, we will want to have a copying function in our functional programs, and we can indeed implement this if we say, yeah, we're actually using 2 times this variable. So this has been a very fruitful idea that has been implemented in several different systems. Idris is one of them, based on quantitative type theory, granular linear Haskell. So that's quite neat because it kind of gives us for free specifications. There's a catch, however, because quite often it's not possible to determine a static multiplicity. Consider this program, which is a program which attempts to extract the head of a given list axis. And in case the list is empty, we'll use a backup element y. And then we'll spit out kind of the head of the list, or a y, as well as the rest of the list. For this to be a linear program, we also have to kind of give back the rest that we didn't use, actually. So our safe head program is just defined by pattern matching, and in case we are given the empty list, then we'll use the y, and we don't have any remaining elements. And in case we actually have something in our list, then we don't even look at the y, right? So in this case, we don't need y, so the multiplicity of y can be really 0 or 1. It depends on the given list. So this is something that we can't capture in systems with static multiplicities. So the point of this talk will be to introduce a way to add dynamic multiplicities, so to give a typing discipline where we can give a precise type to the safe head function. And moreover, we don't even have to cook up a new system because we can add this to an existing dependent type theory. We'll use cubical acta because it has some nice features, but it's actually not crucial to use cubical acta. So we can really carry out this construction in any dependent type theory, and nothing that I'll show you in the following is a postulate or an axiom or anything like this. This is all kind of just cubical acta programming, and it's actually inspired by Gödel's dialectica construction, which, if you haven't heard about it, don't worry about it. But in a nutshell, dialectica is a kind of recipe to turn an intuitionistic calculus into a linear one. That might be one way to characterize it. So here, quote Gödel is depicted pulling out the rabbit out of the hat. So it's a very neat trick that we can employ whenever we need to kind of linearize a calculus in some way. All right, let's make this concrete. So we will make use of cubical acta, and particularly we'll make use of bags or finite multisets, as they're also often sometimes called. And they are in essence just lists where we don't care about the ordering of the elements in the list. So we kind of have, again, a nil constructor for a bag. We have a cons operator, which allows us to put something in front of a bag. We have an append operator, which is just plus in Haskell, but we've suggestively chosen already the tensor symbol here for the append operator. And crucially, because we kind of quotient these lists by reordering, this also means that this tensor operation is commutative. So that's some nice symmetry that already suggests that we can use this for something of some linear logic hacking. And we'll just use these bags that are provided by cubical acta and define the type of supplies, which are just kind of the maximally polymorphic bags in some way. So any value can be put into a supply because we just use this sigma type here. If you haven't seen dependent type theory yet, don't worry about it. We'll just use, I think, 2 sigma types. And the first one is this, which just says, well, really, in a bag, we can put a pair of a type and then an inhabitant of this type. So for instance, this iota allows us for any type A to take an element A and produce a supply. So we'll just put an A comma A in front of the empty supply. And actually, you don't really need to worry about the implementation details of supplies in the following. What matters is that we have this iota, which allows us to turn anything into a supply. So if we have, for instance, iota x for some x of type A, and we also have the iota axis, where axis is a different type from x. It's a list of a's, but we can pack both things into the same supply. And we will only pretty much use the diamond symbol for the empty supply, the tensor symbol, and the iota in the following. So this is kind of all you need to remember from this slide. And the reason we introduce these supplies is that we think of these as kind of the contexts that tell us which resources we can use in a construction. Crucially, they're not contexts, right? They're just some terms living in this supply type, and they do not contain just variables, right? But rather they kind of may repeat variables from the host-dependent type theory, but they can contain any kinds of things. But really kind of what we care about is what variables the supply tells us that we're allowed to use. Okay, so the supplies are the first ingredient that we need. The second one are what we could call productions, which kind of turn one supply into another. So the bag of cubicle acta already has some nice structure. For instance, we said we can just reorder things in a supply. In particular, this means we don't care whether we have an X and an axis or an axis and an X in a different order given into a supply. But we'll also often encounter cases where a supply contains actually an X and an axis put together into a list. So this double colon here is the normal list cons operator. So if we really put X in front of axis and then consider this as a supply, this morally has the same resources as, well, either of these two supplies, right? But this is something we won't be able to prove. I mean, actually, this won't be false, because if you had a length function for supplies, the length of this supply is 2, the length of this is only 1. So this certainly can't be equal to either of these two sides. So we have to kind of introduce a slightly different notion of sameness. And for this purpose, we had these productions. So they're really a relation between supplies. And kind of they inherit the properties of equality. Actually, like most of the productions, you can write down relatively quickly if you're familiar with the categorical semantics of linear logic. So kind of for the experts, you can think of the supplies as the object of a symmetric monodic category, and then the productions are morphisms between these objects. If you haven't heard about the categorical semantics, don't worry. The crucial point being is kind of most of them are actually not very surprising. The only thing that we kind of have to add, which is not maybe obvious, is that we will want to be able to add and remove constructor symbols freely. So I said above, well, morally, this supply here on the right-hand side should be the same as on the left-hand side. Let's capture this with a production. So here is OPL cons, oplux, I'll read it as oplux, says that iota of x in front of axis can be turned into x and then the axis separately in the supply. And we can also go in the other direction with the lax cons production. And we also actually are allowed to just discard the empty list because it doesn't contain any resources. So we have this oplux empty list production, which turns iota empty list into the diamond, and vice versa. And again, there's a kind of nice categorical structure that justifies these productions, namely that iota is strong monoidal with respect to products, but we don't need to worry about this. We just need to remember that we now have supplies and productions, and this is all the structure that we had to add to now be able to talk about linearity in cubicle acta. And we'll do this by looking at this following dependent type, which is just something that we kind of write down exactly like this in cubicle acta. So it's just a definition, which we read as a sort of linear judgment. So like we read this as in the supply, which is kind of a linear context delta, we can derive something of type A using the rules of linear logic. So this is why this entailment symbol is written this way. Precisely if, again, a sigma type, where the first element of the sigma type will be an inhabitant of A. So if we can actually produce something of type A, and also we can produce a production which witnesses that delta contains exactly the resources of A. So kind of we have to do two things, just construct the intuitionistic term, and then also show that this term is really made up of the resources that we're given. And that's kind of the crucial definition. And thereby we can already talk about linearity in cubicle acta. So kind of these two constructions, supplies and productions, and then this dependent type. And now we have everything we need. For instance, we can type our safe head function, which, as you remembered, took in a list axis and an element y. And now we construct something of this linear entailment type. So this here on the left-hand side is the supply that we are looking at, and then on the right-hand side we have the output type that we try to construct. So we want to construct a pair of an A and a list of A's. And the supply is now actually performing some computation, right? Because it's just something that lives inside the type theory. We can in particular just use functions such this null function, which will just give us back a Boolean checking whether the x's is null. And we can represent this dependency between x's and y now in our supply. We can just say, well, we'll need this y only in case our axis is null, otherwise just give back the diamond symbol. We will certainly need the axis though. And then if we implement this SafeHead program, since this is a sigma type, this linear entailment, we really have to give two things. First of all, a witness of A cross list A. So this is the same one as before. So we'll just give back Y in the first case, X in the second case as the remainder of the list here. And the second thing we have to do is now to provide a witness that we've actually used the given resources, right? So we have to construct this production. And now it's very convenient that cubicle acta reduces things appropriately for us. So for instance, in the first case, null axis will reduce to true, which means this will actually, this whole if and else expression will reduce to iota y. So we have something which is almost looking like the supply we have actually available. And similarly, in the second case, where actually this diamond will also be discarded because this OX is implemented in with computational contact in cubicle acta. So this almost looks like we have used the provided resources. We just need to provide some witnesses of this production data type, which aren't super interesting. So we just need to compose some lax, some oplax productions for the different data types, which aren't very interesting. So mostly I will skip these, but it's usually quite straightforward to come up with these. Okay, so this was the construction. Now let's do some hacking with it. So this is Kurt Gödel depicted how he might have looked like if he had lived 100 years later. And his immense power is apparent by the fact that he's able to look through the screen and code. And maybe this would be the kind of programs that he would have written. Because we're now using this dialectical construction in cubicle acta to program. We've already actually seen something quite cool with the SafeHead function. Let me go back. Because we've deconstructed this axis here, right, to produce something. So we've kind of used an elimination principle for axis, an elimination principle which treated this list appropriately as a resource. And we can generalize this to derive linear elimination principles. So we didn't have to talk about linear elimination at all, right? When we set up our theory, we only talked about constructor symbols, but it turns out actually we get these linear elimination principles for free. So let's introduce this abbreviation, like these aren't really linear functions from A to B. They're kind of just working in a similar way. They're really dependent functions which take an A to a witness that X can be turned into B linearly. But these kind of work like functions. So we can, for instance, apply these with add. And then we can implement a fold principle for lists, which is a linear fold principle, because we're now giving a const function, which is linear. So it takes an A and a B, uses both to produce a B. It has a nil case, which just has a B being produced from a delta. And then the linear fold principle, or actually a linear fold principle, this is why there's a 1 here. There's in general many sensible elimination principles you can give in a linear setting. A linear elimination principle would turn any list, and using this list once, as well as the delta, which is needed for the base case, into a B. And we can just define this fold R1 by pattern matching, or actually dependent elimination is what's at the core here, using kind of our add function, and there's like some syntactic sugar that is needed to like kind of lift everything from an intuitionistic level into our linear level. But crucially, kind of this works just in the way you would expect a fold to work. And this requires some work, like this by ... means we had to apply some production, so there's some bookworking that needs to be done. But we can use this fold on functions such as a linear insert, and this gives us a insertion sort, which we know will not drop or duplicate any elements because it's in this linear system. And it's defined in exactly the way you would expect. It's just a fold of insert on the empty list, where again, this is kind of the empty list considered linearly. So we don't have to do any more work. So I think this is quite neat. And yeah, I think what is nice from a theoretical point of view is that we didn't have to like think about data types linearly, really, because they kind of can be treated linearly just by using dependent elimination. Okay, the second thing I wanted to mention is that we now can also really cash in on the fact that we can compute in our supplies by introducing something which looks really like multiplicities in other systems, where we don't have to add any more structure, but we can just use the built-in natural numbers of ACTA to draw multiplicities from. So we don't have to impose an additional semi-ring on the structured rules or anything like this, because we work in this ambient type theory, can just use this type theory to compute resources for us as well. So, for instance, we can cook up a fold R2, so a different kind of folding principle for lists, which has a slightly more involved cons case, where crucially in the cons case, we make use of a delta 1 supply. So in each step that we're folding our list, we will need to have we are using some supply delta 1, which means we'll need this delta 1 as many times as our list has elements, right? So this is why this exponentiation function here was introduced, which is, again, just kind of an inductive definition in the host-dependent type theory. Like, there's nothing fancy going on. It's really just taking n copies of a given supply delta. And we can use this here to give a precise type to this linear fold for lists. Namely, it will use the delta 0, which is used in the null case of our fold, and it will need length axis many copies of our delta 1, which is used in each of the cons cases, as well as the input list to produce a B. Again, the definition follows kind of relatively straightforwardly once you use kind of these new primitives in some way that we had to introduce in our system. And again, we can use this, for instance, an interspersing function. So this is quite neat. But we can also use other types to represent multiplicities. So one other interesting type would be the connatural numbers, which have not only 0 successor, but also an infinity term, which is equal to itself, the successor of which is equal to itself. So we can again define such a exponentiation, now co-inductively, of course, because this is a co-inductive type. We can even, like as a nice syntactic sugar, have kind of function types which take in a connatural multiplicity, so A, and then m copies of A will be needed to produce a B, precisely if this dependent type here is inhabited. And using this, we can write quite nice functional programs. So, for instance, an iterate function, which takes in a linear function from A to A, and then it will need the input A infinitely many times to produce this iterated list. Okay, so this was programming in the system. Let's wrap up. I think you have some laksa to eat. You can tell I have a bit of FOMO. So here's Pierre-Martin Löw, Jean-Yves Gerard, and Kurt Gödel, how they would have maybe looked like when they had attended ICFP this year. So let's summarize quickly. So we've seen this recipe, so just a way to encode in cubical ACTA this dialectica translation, giving us a linear typing discipline. And you can also carry this out in the other kind of theory, actually, without bags. I think what's neat about it is that linear elimination principles are just admissible. The caveat is we don't really have function types yet. I wrote the lollipop in some places, but it's really more syntactic sugar. There isn't really function types yet. But the upside is we can compute in our supplies, and thereby we can give precise types that we can't precisely type in other systems. And that was heavily influenced by a talk by Pierre-Marie Pedreau last year in Tallinn at Transcendental Logic and Applications. And recently I've learned about some model construction by Robert Adke, which actually is very similar to this linear entailment. So this is kind of just on the semantical side. So one way to look at this construction is also that we use cubical ACTA in some way to internalize some of the semantics of linear dependent type theory, and thereby we obtain this powerful theory. Okay, let me very quickly say what is next to be done. So I have an idea how to end linear function types, and also these productions are tedious to write by hand, so we can do this actually, I think, automatically. So there's a preprint with work in progress if you're interested. Let me just give a huge thanks to Pierre-Marie and Valérie de Piper as well, who introduced me to dialectica, and many others I've talked to and also in particular the SFP reviewers, who gave some really, really helpful feedback. Thanks a lot.
Excellent. Thank you so much, Maximilian. Let's we've got time for one question, I think. So, thank you so much, anyone in the room? Okay, I will ask a question. So, when you showed the safe head example, I, as a granule guy, immediately thought, well, I would give it the type with 0 to 1. I would use granules semi-ring of intervals over natural numbers, because then you can say it's 0 or 1 usage. And in Granule, you can combine semi-rings together, so you can do like intervals over semi-rings and things like that. So presumably, you can essentially have, like Granule, a kind of algebra of semi-rings quite easily then to generate new kinds of supply in your setup.
Yeah, sorry, I'm probably a bit delayed because I have to listen to the audio on YouTube. To answer your question, so absolutely, so in Granule we would probably give an interval, like we would use this either 0 or 1 times, which of course also works, but kind of this doesn't fully narrow down the space of possible programs. So in some way it still allows a faulty implementation of SafeHead where you just always give back the Y possibly. Sometimes at least. I think it would also be interesting to study different types to use kind of for these exponentiations. So I think there's certainly room for affine systems as well in this setting, or to possibly also have some interval types by which we take exponentiations.
Yeah, cool, great, thanks very much. Okay, let's thank the speaker again. So we're going to be back in the room, and we're going to think positive with binary search, thanks to Alexander Dingus. Over to you. Okay, we need to think more positively until it shows up. Hey.
What is that? That's on your screen?
No, on my screen there's
nothing on. I see it. No. Oh. Oh.
Okay. So you can, I think, relax a little bit. Can't hear you. Be quiet.
Okay, it's okay, perfect. So now you can probably relax a little bit because you're all familiar with the topic. Binary search, it's really old, and it's essentially so old that already the Babylonians used it, at least some kind of some intuitive form of it, for there were some tables found with reciprocal values, and the pairs were ordered so that instead of computing them by hand, you can find them by, as I said, an intuitive form, like in a phone book, of binary search. So, and indeed, binary search is hopefully known by every computer science student. We teach it in every algorithmics course. And yeah, so let's have a look at two examples of two definitions of binary search. So the first one is from Donald Knuth from The Art of Computer Programming, and it's along the following lines. So assume we have a table where we have keys k1 to kn, and we assume that they are sorted. And now, given a key k, we search for an index I such that ki is equal to our search key k. So that's the problem description. And now how is binary search performed? So we pick an index between 1 and n, and we compare k to km, and there are 3 possible outcomes. So the first outcome is k could be less than km. In this case, we eliminate the keys km from kn from consideration, or we could be lucky and k could be equal to km. In this case, we are done. Or k could be greater than km, in which, so this is the dual case, so the first one, in which case we eliminate the keys k1 to km from consideration. And now to the binary part of binary search, if we pick the m to be the midpoint, then we get logarithmic running time. So that's one definition. Then a second one from Introduction to Functional Programming by Richard Burt and Phil Wadler. It's a bit different. So now here we have again, and I forgot, of course, to say that we recurse then, in this case, by after some possible re-indexing, and in the base case, well, that's trivial if we have only one element. So now, Introduction to Functional Programming. Similar, we have an interval L to R, and now we have a predicate P. So I'm using actor syntax here, so we don't go from n to bool, but from n to set. So, but we search the smallest index I in L to R such that Pi holds, and of course we assume that P is monotone, and so again, that's the problem. And now how is the algorithm? We again pick an index m in the search interval, and we check PM. Now there are 2 possible outcomes. Either PM holds. In this case, we eliminate the indices 1 plus m from R from consideration, or PM does not hold. In this case, we eliminate the indices L to m from consideration. And again, for the binary part of binary search, if we pick m to be the midpoint, we get logarithmic running time. Of course, there are many differences between those 2 definitions, but there are also, they share some points. Of course, the binary part, choosing m to be the midpoint. Also, we proceed, of course, recursively. And also, in each recursive step, we eliminate roughly half of the search space. And I think most importantly, both assume some kind of monotonicity. So in the first one, we had that our keys were sorted. And in the second one, we assume that our predicate P is monotone. So now you can open your favorite textbook describing binary search, and probably the definition there will be somewhat similar to one of these definitions. And now you can go a bit further in the textbook and open the exercises for this chapter, and you might find the following exercise. So, the following exercise: you are a contestant on the game show Beat Your Neighbors. You are presented with a sequence of n boxes, each containing a natural number. It costs 100 euros. To open a box, your goal is to find a box whose number is larger than its left and right neighbors. If you spend less money than any of your opponents, you win a week-long trip to Berlin. Actually, this exercise is from Jeff Erickson's book on algorithms, and it's not in the on the part of binary search, but this sounds better than saying find a local maximum by with as few lookups as possible. So, but there are textbooks that have such an exercise for binary search. However, this does not fit the definition of binary search. So the reader is, of course, expected to adapt binary search to this exercise. So let's try to solve this on an example. Assume that these are our boxes. And of course, we have to say what happens at the very left and very right. So we assume that we have virtual boxes containing 0 at the very left and very right. And of course, we say that greater is greater or equal. So now let's draw the values, and we are interested in a local maximum. So actually, for a local maximum, the only thing that matters is the slope, not really the absolute values. And now, why is there even a local maximum? Well, we assume, because we have these virtual boxes at the very left and at the very right, that the very left slope is non-decreasing and the very right slope is non-increasing. So in between there must be a local maximum. And now let's just look at the middle slope, and now it's again decreasing, so we know that there is again a local maximum on the left side, and we do the same again. We look at the middle slope, and then we are done in the end. So we have found the local maximum by binary search. And so for understanding why this works, let's have a look at an even simpler example, which is very, very similar. So here we have the task of finding an even odd pair. So we have given these boxes here, and the task is to find an index I such that the box at position I is even and the value at 1 plus I is odd. And this actually fits the description of binary search we've had earlier. So we have a predicate that's monotone. In this case, the predicate is odd. It's a bit different in this case, since we are looking for a pair, but this shouldn't bother us. So let's perform binary search. We look at the middle value, and it's even, so we remove the first half from consideration. So now we look again at the middle value, and it's odd, so we remove the second half from consideration, and so on. And in the end, we find the even odd pair. So let's do the same example, the same values again, but we shuffle them around. We have now no monotonicity given. Nonetheless, we just perform binary search as we would before. So we start at the middle. We have 5. 5 is odd, but we can't talk about anymore about removing the right half from consideration, because obviously there are 2 even odd pairs at the right half. Nonetheless, we just go to the left half as we would before. We look at the middle value here. It's 10, so it's even. Again, we can't really talk about eliminating left half. There's again an even odd pair there. Nonetheless, we go right and we perform the binary search and we find the even odd pair. Why did this work? So did I just choose a good example? So let's formalize this in ACTA to make sure that this really works. So we have a function, even odd pair, which takes our interval L to R. We model our boxes as functions from n to n, and we promise to return an index I such that box I is even and box 1 plus I is odd. So let's first make the recursive step. We model our search interval by a tree, but so we have this M is, you can think of M as the midpoint, T is the left half, and U is the right half of the interval. And we check now the parity of the box in the middle, and there are 2 possible outcomes. So it could be odd in this case, just by our recipe, we go left, and if it's even, we go right. So so now let's look at the base case. In this case, well, we can't recurse anymore. We have to return something, and we can't pull the rabbit out of the hat. So the only possibility is that we assume that the box at position n is even and the box at position n+1 is odd. So we assume this here. So we assume that the leftmost box is even and the rightmost box is odd. And in the base case, we just return this. And in the recursive case, we have to adjust a little bit, but that's exactly what we are checking here. We check the parity of the middle box, and now, we have this. We have that the middle box is odd, so we go to the left one, and now the rightmost box is odd, so we can recurse. And so what we have here actually is a very simple example of an invariant. So we start with our boxes. The leftmost box is even, the rightmost box is odd. We look at the middle box. If it's odd, we go left. If it's even, we go right. So we maintain the invariant after we have looked at the box at the middle. And in the end, if we have only two boxes left, then the invariant gives us already the result. And actually, that's exactly what's also happened with the beat your neighbors example with the local maximum. So in this maximum here, we were guaranteed to find an even odd pair, and for the local maximum, this was the case as well. So, and we can now abstract away from even odd or local maxima. We can say binary search is the following function. We have an interval L to R, and now instead of looking for even or odd or for the sign, we have just any oracle, and we have any two predicates P and Q, and they don't have to be even exclusive, just any two predicates P and Q, and this decision procedure oracle, and we assume that at the leftmost point L holds at the leftmost box, or at the leftmost point P holds, and at the rightmost box Q holds, and we promised now at the end that we return an I such that we have Pi and Q1 plus I. And the code below is really the same as for even odd pair. We just rename, and we have oracle now as an extra argument. So you see that we don't eliminate anything. We just go where we for sure find a solution. So we think positive, therefore the title. And we don't assume monotonicity. So binary search has nothing to do with monotonicity. That's the point here. So why then why almost all definitions of binary search assume monotonicity then? Let's go back to the very first definition from Knuth, where we have the problem of table lookup. So how does table lookup look in this new framework? So again, we have an interval L to R, and we model our table as just a function from n to n. We have our search key. And now, instead of looking for equality somewhere, we first, we promise to return an index I such that table I is less than or equal to key, and key is less than table 1 plus I, provided that key is greater than the leftmost point and less than the rightmost element. So in traditional binary search, we search for equality, not for two inequalities. we want an I such that table I is really equal to key. And of course, it might be the case that there is no such I. It may fail, so we have actually a decision procedure. But so in this case here, we always succeed, yeah, but we somehow give less. So, but we didn't assume monotonicity yet. So let's assume monotonicity. And so the only thing that we add here is monotonicity. And now we can actually decide if there is an I, yeah, such that table I is equal to key. And the idea is pretty simple. So table I, we have this, we have this proof here, table I is less than or equal to key. And now we look into this proof and we check. If it's really an equality proof, then we are already done. So table I is really equal to key. And if table I is strictly less than key, now in this case, we use monotonicity to rule out that there is nowhere such an index I such that table I is equal to key. So monotonicity is actually only used in a post-processing step. It's not really used for binary search. So yeah, let's wrap this up. So in traditional binary search, we look for a single index, but actually what the right way to do is we should look for a pair of indices of two predicates rather than only one predicate. And we don't rely on monotonicity, but really on an invariant for the leftmost and rightmost point of the search interval. And we don't eliminate, so monotonicity allows us to eliminate, but actually that's not the right way. You should think positively and focus on where you can find the solution. And therefore we are always successful in comparison to traditional binary search, which of course may fail. So as the conclusion, binary search has nothing to do with monotonicity. It's about this invariant, so yeah, think positively. Thank you.
Great, thank you, Alexander. Let's take some questions. So, am I right in thinking that kind of one of the key things is defining this interval? Because that seems kind of important with the between L and R. Like, it seems important to then kind of understand the relationships and the underlying data, right? Because in the beat your neighbor, or no, sorry, in the odd even case, you could have a data set which was sort of all odd or something like that, right?
Assume at the first place that you have so that you at the rightmost point is odd and the leftmost point is even. You could of course check this before you run binary search, and I mean if this doesn't hold, then there is no point in even running binary search.
Yeah. So the assumption would be false, and then yeah.
That was my question.
Right, okay, great. Next question.
In your first two examples, they differed by the worst case was, so logarithmic was the worst case in the first example, while all the cases were logarithmic in the second example, right? In the beginning of your talk. So can you say something about best case and worst case scenarios and average scenario for your version of binary search? I mean, this version of binary search, okay, I didn't talk about the interval representation here. So actually, the only thing about the binary part and the logarithmic running time is only running time improvement. So here, if m is really the midpoint, which this type in this case doesn't really force, but if m is the midpoint, then we have logarithmic running time worst case as well, yeah.
Okay. Any further questions? Okay, well, I will, before we thank our speaker, I will encourage you all to check out this paper because it has a very entertaining style as a dialogue between a tutor and a number of students. And this is a kind of really lovely way to take you through the paper and kind of explain binary search in a sort of a completely different, well, in a completely different way to, I think, sort of most presentations actually. So it's like extremely illuminating, gives you a new way to think about a classic kind of algorithm. So very cool stuff. Thanks, Alexander. So that brings us to the last talk of the session, and indeed the last talk of ICFP, well, the last concurrent talk of ICFP, because there's 2 ICFP tracks happening. Okay, excellent. Do we need to change the color, or is that okay?
It should be.
The true tone.
I don't have it enabled, so.
We need it to be in false tone.
Yeah, that's.
Maybe
Yeah, that's what it looks like here. So I don't know. Is it okay enough?
Yeah. I think it's fine.
Yeah.
Great. Okay, so we're going to be hearing about teaching software specification and experience report, thanks to Cameron Moy. So over to you.
Okay, great. Yes, I'll be talking about, teaching software specification. This is work done with Daniel Patterson, who is a professor at Northeastern. I should also say that if you find the topics in here interesting, and also your institution is hiring, I'm on the academic job market, so please find me later if that's the case. Right, so this is an experience report. It's not a full research paper, so I really want to give people a couple of takeaways that you might be able to use in your own courses. Okay, so I think we're at ICFP. This should not be a particularly controversial statement here, which is that software specification is important, and it's so important that it shouldn't wait until much later on in someone's experience in undergraduate. It should be prominent in the first year, and maybe even in the first course. And this is something that we've certainly believed in at Northeastern for many years, long before I got there. And this is what the curriculum has looked like at Northeastern for a long time. This is the first couple of years, depending on how long students take, perhaps the first 2 or 3 years. And the first section here, which I've highlighted, is the first year, typically. And this first course, Fundamentals 1, and second course, Logic and Computation, both focus quite heavily on specification, software specification, among other skills. So in Fundamentals 1, there's this systematic program design philosophy, which is centered around something called the design recipe. So if you're interested, you can look at the How to Design Programs textbook. And in that philosophy, specifications are given as informal comments. So whenever you design a function, one of the key components is to write a signature and also a purpose statement for every function. And that's done in a pedagogic language called the beginning student language and the intermediate student language. But it's all informal, it's all in comments, which is quite good because it gives students the flexibility to describe specifications as they see fit and not have to describe it in a particular static type system, for example. But of course, we want to get a little bit more formal. So in this second course, this Logic and Computation course, we have students actually write formal specifications, formal properties, and then they prove that a particular piece of code is correct with respect to that property. Depending on the instructor, the proof assistant may be different, but primarily in the last few years, that's been in the lean proof assistant. Okay, so I want to talk specifically about this second course, this Logic and Computation course. Now, what happened was Daniel, he was a new faculty, the co-author on this paper, and he was teaching this course, and he was telling me a little bit about some grumblings that he heard from some of the students about his course. So we decided to do a little bit of a more formal interview process and asked them what they thought about logic and computation. Okay, so I have a few quotes, and maybe if you've taught a similar kind of course, you might have heard some of these things before. So let me read a few of them. The way we practiced felt like a game to find the correct keywords, really tactics, to make Lean happy. I know a lot of people in that course were really just programming by trial and error. I'm not sure it taught any practical applications to prove software correct. And I wouldn't be able to apply directly anything to test real-world software applications. Okay? So, I mean, a lot of the students in our undergraduate program, they are looking to become software engineers. And this is kind of disturbing to us because we think, well, software specification is very much a relevant skill to our students. And they're coming away from the course thinking, well, all of this is useless, I don't know how to apply this, and it's all about, I guess, mashing random tactics into the proof assistant. So that's absolutely not what we wanted to hear from the students. And certainly not every piece of feedback you get from undergraduates is going to be relevant, but if this is the takeaway from the course, that's a failure on us, I think. Okay, so we wanted to do something different. So I'm going to describe a couple of lessons, 5 lessons from a redesign of this course, and hopefully it'll be something to take away. Some of them are a little bit specific to our setting, but I think all of them can perhaps fit with some adaptations in other institutions. Okay, so very briefly, the 5 lessons from this redesign. The first is to give assignments inspired by real-world software. The second is to emphasize software specification skills as opposed to formal proofs. Third is to use lighter weight means of checking the conformance of the properties. So in our particular case, using contracts and property-based testing, and a heavy emphasis on that. The fourth is to tailor a pedagogic language for the course. So remember, we're focused on freshmen here. So having a language to do that and to minimize the kind of distractions. And fifth is to address skill transfer into other programming languages and environments very explicitly. Okay, so I'm going to go through each of these in turn. So I think maybe one of the most important things from the redesign is an emphasis on real-world examples. So I think one of the failure modes in the prior iteration of the course is that when you're trying to do proofs, and we have freshmen, and it's really kind of also an introduction to formal proofs, you can't really get too far. Maybe the most complicated example that they do in that course is proving the correctness of some sorting algorithm. But typically a lot of the course is spent on basic properties, say commutativity of addition, or associativity of a list append, those sorts of things. And they never actually really get far enough to see the value of software specification in more real-world applications. So the assignments that we chose, and I think a lot of the learning happens in the assignments, as in many courses, are chosen from as many domains as we could think of, and are modeled after real-world situations. So they're toys in a lot of ways, but there's some kernel that is in the real world. So for example, we have an assignment which is inspired by security, having a specification for timing side channel attacks, and having students fix a function that's vulnerable to that. We have a PL-inspired assignment, which is about the correctness of a particular optimization in a compiler to a stack machine. We have an assignment which is based on game design, which has a bunch of different representations of mazes, and then round-trip properties between these different representations. We have an assignment which is inspired by systems programming. So we have students write a very basic memory allocator, and then write down specifications talking about the correctness of that memory allocator. And then finally, I think my favorite, we have an assignment that is inspired by distributed systems. We have students implement the Chanty-Lamport snapshot algorithm and then talk about correctness properties of that algorithm. Okay? And we can do this in the freshman year, which is pretty cool. And I think the only reason we can have those kinds of assignments is we're focusing very much on specification and not on proof. Okay? So this is kind of the philosophy of that approach, which is to have a gradual increase in confidence that software conforms to your specification. So we're not going to insist on being fully verified at the very beginning. This is a kind of gradient that we have. On the left-hand side, we have something like runtime checking, where you describe the property and check it during the execution of a program. The second one is maybe a little bit more so. We have property-based testing, where you can test whether or not a program conforms to the specification based on many, many possible randomly generated inputs. And then finally at the end, and we do this a little bit in the course, it's only in the last 2 weeks, but we would like students to actually see it, is verification and a proof assistant. But we're mostly focused on the first two, and that's how we're able to get some of these more realistic and more challenging kinds of specifications in the assignments. Okay, so what are the tools that we're actually using in order to do these lightweight conformance checking? The primary ones is contracts and property-based testing. So let me show you a little bit of what that looks like for the students. So here's an example program that a student might write in Fundamentals 1, which is the first course. It's this only non-negative function. And you'll see the important part is at the top. So I mentioned earlier there's this design recipe, and there's this step, which is the signature and the purpose statement. So we make sure that for all students, they're writing these as comments. We can see the type signature, list of integers to list of naturals, and then the purpose of this function. Okay, so this is what they do in the first course. And what we want to do is we want to make a very small change in the next course from this. And it might be small enough that you might miss it, but now it's a contract, okay? This is no longer a comment. This is actually a piece of code. And what we can do is we can use that contract in order to get some benefits. So of course, going from the informal to the formal to the contract might require some additional work on the student's part. So these are built-in contracts, but perhaps if they had an informal comment that was describing a property that wasn't provided by the standard library, they would need to write their own contract, their own predicate in order to check that property. But by having a contract here, we get some nice benefits. So what's an example? Suppose that you messed up this function. So now it's the identity function. It's not actually performing what you think it is. The contract will be able to tell us that. So for example, if you're in the REPL and you give it an input, this is going to give a contract violation because -1 is not a natural number. And that integrates well with the IDE as well. And we can also do property checking. So the language provides this check contract form, which knows about the contracts that are associated with each function that the student writes. And for the input positions, it's going to use a generator, which is associated with the list of integer contract. And then it's going to check the outputs. So here, after trying some amount of time, it produces a counterexample here, which is a piece of code that the student can then copy and paste and put into the REPL and then reproduce a contract violation. Okay? Now, of course, if the student is using some custom contracts that they've written, this also might require a little bit of extra work to write generators for those contracts. But you get some nice benefits from that. And all of this is relatively lightweight. Okay, so I've been showing some examples, but of course all of those examples are in some programming language, and the programming language we've chosen is a custom one. So let me show you this diagram here of the curriculum, and annotated are the programming language that the students are using. So in Fundamentals 1, it's this series of pedagogic programming languages, from beginning student language, intermediate student language, and then in the old version, it's a complete jump from this intermediate student language, a baby language, all the way to lean, okay, which is it's a bit much, a bit of a gap. So what we've done is we've developed an extension to this intermediate student language, a strict superset of its functionality, to provide contracts, property-based testing, and actually quite a lot of other features. So you remember I mentioned earlier that we have this distributed snapshot assignment. One of the only reasons why we can do that is because there is a lightweight concurrency mechanism that's built into the programming language, which is based on some of the features from the intermediate student language. So if you're familiar with how to design programs, there's this thing called Big Bang. We have a version of Big Bang that allows students to write concurrent programs by specifying actors purely functionally. Okay, and it makes it very easy for students to write that. And otherwise, if we had them doing this in Java, it might be quite difficult. Okay, so why a pedagogic programming language? Well, we can customize it and make it very smooth for the students. So they get to use the same IDE, the same syntax that they are familiar with. We don't need to reteach them functional programming. They can, on day one, start learning the skills that we're trying to teach them. So here's one example of what you can do when you have a custom programming language. So on the left-hand side is a data definition from Fundamentals 1, which is describing a binary tree with data at each of the nodes. And what we've done is on the right-hand side is a contract for exactly the same data definition. And the key thing to note is that it looks very, very, very similar to the thing on the left. And in fact, we've designed the API for the contracts to try to mirror the language that is used in the data definitions in the textbook. So this is just one example of the kinds of things that you can do when you're developing a pedagogic language. And we make heavy use of all of these analogies between the earlier course and then the later course. Okay, the final thing that I want to talk about is skill transfer. So one of the things that I hear often with students who are using these pedagogic languages, and other people who teach from how to design programs probably have a similar experience, which is, this isn't real, okay? This language is a baby language. I feel like I have the tricycle instead of a bicycle, right? The training wheels are still on. I want to see what programming looks like for real. And that's very, very true. So we have some assignments that explicitly tell students to go outside of the teaching language and find a property-based testing library and try it for themselves. They can pick any language they want. Most students pick Python or Java or JavaScript, but they can pick any library they want and to redo some of the homeworks in that library and see how it works in the real world, so to speak. And it's funny, often students come back and say, oh, I liked your language much better than the existing ones. It's much easier to use. But they come back thinking from this that, well, this is actually tools and techniques that I can use when I go out on my internship or at Northeastern co-op program. Okay, so we also interviewed students who took our version of the course. Now, this is not a research paper. This is an experience report, so this is not a super scientific accurate reporting, but we tried to get a representative sample, both for the students who took the prior version of the course and the one that we'd redesigned. And basically across the board, the things that students said were quite different in the version that we taught, the redesigned version. So here are some. When I took the class, it changed my perspective quite a lot. I never really thought about the correctness of programs before. My main takeaway was the importance of testing your code. Testing thousands of inputs quickly was very, very useful. The contract that we used helped a lot with making sure that all of the inputs were valid in the functions that I wrote. And I think my favorite one from the students was being able to make sure the work you're doing is correct and does what you actually want it to do is pretty important. And they were describing not just software engineering, but basically any job. And the course helped them think through that. So this is very, very different from what we heard initially, and we were happy to hear that students didn't think that all of these skills were useless. They thought it was relevant to their future job prospects. And also, we had concrete tools that they could use when they went out. Okay, so to summarize, here are the 5 things that we did differently in the course. Giving assignments based on real-world software situations, emphasizing specification skills over proof. Not to say we didn't do any proof, we did a little bit of verification at the end, but most of the course was spent on the skill of software specification. Using lighter weight specification tools like contracts and property-based testing, which especially property-based testing is very, very common now, or more common in software engineering practice. Tailoring a pedagogic language for the course, and this is especially important for freshmen. But that comes with some risks that we try to mitigate by addressing skill transfer into real-world programming languages explicitly. Okay, so there's more in the experience report that I didn't mention. I think these were just the highlights. There's a description of the course topics, basically the entire syllabus that we have. Some other interesting contracts. So my research is in contracts, so we had students specifying some of these interesting properties using all kinds of contracts that you might not have heard of for data abstraction, contracts on mutable data structure, and my favorite, contracts about temporal properties, so specifying some protocols. Some ideas about how to adapt these lessons to other settings. And also, we have an artifact associated with the experience report that has the software, the assignments, and all of the lecture notes. So if you want to steal any of the material, if it seems relevant to your courses, please do so, and we would love to hear from you if you do. Okay, that's all. Thank you.
Questions? So Matthias Verleisen has a nice blog post ranting about being forced to switch to Python for the first year course.
Yes, indeed.
So how does that affect this subsequent course?
Yes, so one of the things I emphasized was I hope that this could be adapted to other settings. So it also has to be adapted to our own setting. So we ran this for 2 years. And now we're going to have to change some of the specifics that we have. So the pedagogic language that I developed, no longer relevant. We're going to have to take some of the lessons learned and adapt it to whatever is going on with the new coursework. I'm not going to worry about it, but I know some of the instructors who are taking over, they're thinking about it and using some of the lessons that we learned. Yeah.
Okay. Commiserations and good luck.
Jared Gettner, unaffiliated. Cameron, something finicky about contracts, and I just want to know if this has come up. Something finicky about contracts is contract performance. It's an observable thing, and if like a student is having performance issues and they find out it's because a contract is being checked over and over again, that really like muddles the lessons and makes it a little bit too complex for a starting out student. Have you seen or run into that at all?
So, I mean, we were pretty careful when we designed the assignments such that they're small enough where we never run into performance problems with the contracts. And of course, that's something that when you go into the real world, when you're using contracts a lot, is something that to keep in mind. But for the course we had, we didn't end up talking about it. And as far as I know, it didn't really come up.
So it's like more a matter of careful design of the course?
Yeah, yeah.
Okay.
Hi, really cool talk. I'm just wondering, because you use contracts, do you have any anecdotal experience how people kind of transition to a statically typed language? Because it allows you to write stuff that really, like that identity function example, you wouldn't be able to write that in a statically typed language rather than, you know, only getting the error at runtime. And so even transitioning to Java, have you seen kind of issues where you have just at time of definition, it's more restrictive?
Yeah, so we want our students to see both. So I guess in that picture I showed very early on, typically our students are taking this logic and computation course at the same time that they're taking a traditional course in Java. And in there, it's also an emphasis on turning those type signatures into real types in Java. And so students will see both of them. The expressiveness of contracts is a little bit greater. It has different trade-offs in the types, but all of our students see both, essentially. Yeah.
Okay, thank you.
Hi, Harry Goldstein, University at Buffalo.
When you send students out and then they come back and they say they like the teaching language better than what they saw out there, are there specific things in either the specification language or the property-based testing libraries that they often say is the thing that they like better about the teaching language?
Yeah, so what I remember hearing most of all is in our language, in order to actually run the property-based testing, you say check contract, you give it an identifier, and that's it. It just runs. Whereas I remember a bunch of students when they were using some of the Java libraries, they spent hours just trying to figure out how to get the jar thing in and configure it and figure out the documentation. And so all of that was, and we're talking about freshman students, so part of it is just inexperience. But yeah, it was all of the hassle surrounding using some of these libraries.
Great, thank you.
Hi, just let me know if you've already sort of talked about it, but when you say it's a pedagogical language, what are like the technical downsides of the teaching language compared to, you know, like a so-called real language? Like, is it performance or is it like language features?
Yeah, so the language features are much smaller. So for BSL, it's essentially like a lambda calculus with some extra features, and our language is also pretty small. So it's something that students can understand really in an afternoon. If you look at the documentation, if they already know the intermediate student language, they can read the documentation for our language in a couple of minutes and basically know all of the features. Right. And that gives some other advantages, like the error messages, for example, are in terms that students can understand. There's lots of advantages there, but yeah, there are some disadvantages, and performance is one of them. Yeah.
All right, thanks.
Hi, this is really cool work. I was wondering, you talked a little bit about the gradient from like property-based testing to where like you're improving kind of software, and I was wondering, like, when you kind of move students to using some like proof assistance for some of the assignments, like, did you provide additional scaffolding when teaching them to try to get them there, or was it pretty natural, the transfer of skills?
Yeah, so I mean, I think there was still a lot of the same issues, learning a new IDE, so Visual Studio instead of Dr. Racket, learning the syntax of Lean, for example. But some of the core skills, which is about, you know, what is a specification, what does it mean, what are we doing here, they understood that by that point in time. And so they were maybe a little bit more motivated.
Cool, thanks.
You mentioned a little about property-based testing.
Yeah.
Another sort of buzzword out there is test-driven development. Do you do a lot of that? I mean, do you get your students have written a specification? And of course, this is big in Matthias's books too,
Yes.
right?
Yes.
So do you get them to write lots of tests before? Can you persuade them to do that, or they don't see the value?
So the expectation for our students is they follow exactly the same design recipe that they learned in Fundamentals 1 when they're completing all of the assignments. So, and that includes writing tests or examples before writing the code.
Before writing the code,
Yeah.
okay.
Now, of course, do students actually do that? But they're supposed to, certainly, yeah, and we encourage them. Yeah.
I see, right, so you may need some pretty serious mechanisms to encourage them to
Yeah,
do that.
yeah.
Well, that takes us perfectly to the end of the session. Let's thank Cameron again. Remember that he is on the job market, so if you're looking to hire someone, talk to Cameron.